Welcome to Machine Learning for Mere Mortals, an accessible guide to machine learning using Python. I'm Nick Chase and I'm your instructor. I'm glad you have the foresight to realize that machine learning is taking over the world and that you need to get out in front of it before it's too late. Whether you define too late as getting swallowed up by a changing labor market or battling Skynet for the survival of the human race, that's entirely up to you. But let's face it, even though the technology is still at a pretty early stage, it's mixed into everything from what groceries you see on the shelf to how your car is built. I mean, you get up in the morning, you check your email, and you've already had messages blocked by spam filters. You go to Facebook, and it's their algorithms that have decided what you are going to get to see. You get in your car and you go to work, and chances are you're driving on roads that are being analyzed to create optimal traffic patterns. Oh, and the songs on the radio during your commute? They come from artists largely signed based on machine learning data based on sales. You get to work and your paycheck comes from sales generated from various automated customer relationship management solutions, most of which involve machine learning in one form or another. But you're bored, so you decide to go find another job. You go searching some of the job sites and the results come from machine learning. And also, by the way, your resume gets forwarded to recruiters based on, yes, you guessed it, machine learning. You leave work and on the way home, you stop off for some food. And even though it's crowded, there's really not much of a wait because that morning software alerted the management that based on the time of year and the weather and a bunch of factors that you don't know anything about, they're going to need to put on more staff for the day. I could go on and talk about fraud detection and cybersecurity and all kinds of other places we're seeing machine learning these days, but you get the idea. The important thing here is to understand that machine learning is not going away, and it's not something you can ignore. It already controls everything from what programs Netflix offers you to what products appear in your local big box store. And it has the potential to influence even more important things like government policy and the behavior of everyday objects in your life. So even if you're an optimist and you're not worried about living under robot overlords, you've got to know that this is where a lot of the tech jobs are going to go, either directly or indirectly. So you need to understand how this works. So before we get deep into exactly what makes up machine learning and how to make it work, we need to cover a burning topic. Is there a difference between machine learning and artificial intelligence? Unfortunately, it depends who you ask. Artificial intelligence is about getting to human-like decisions using computers, and machine learning is about making it possible for machines to learn to handle situations they may not have seen before. But that's about where the agreement ends. Some people say machine learning is a way to implement artificial intelligence. Some people say machine learning is the only artificial intelligence. Some people say they're completely independent of each other. And that's just the experts. In our case, we're going to look at machine learning as a special case of artificial intelligence. Let me give you an example. Back in the early 1990s, I worked in what was then known as an interactive agency. We built sales presentations and kiosks and things, and I had begged my boss to try and get us into this new thing called the World Wide Web. Now, my boss at the time was a brilliant guy, never did anything in a small way. So the first potential customer he brought us was a huge telco, and it was a $250,000 job to do a complete e-commerce application, complete with dynamic content, or as they called it then, web pages on the fly. All we needed to do to seal the deal was a demo. There was just one problem. None of us had the first idea how to do that. But, we were smart guys and gals, and by the next morning we had a web page that would let the user choose a phone in one of 3 different styles and 3 different colors, and it would display a shopping cart based on those choices. Now, that sounds pretty intelligent, right? Well, thing is, behind the scenes, it was just a giant Perl if-then statement with 9 cases in it, each of which displayed the complete checkout for that combination. So in that one situation, it was absolutely intelligent. For anything else, it was totally useless. Does that count as artificial intelligence? Some people would say, no, that was just a programming trick, and maybe it was. But if you define AI as being focused on providing the result a human might have provided, that was, in fact, a case of what's called narrow artificial intelligence. Okay, it was very narrow, but that's beside the point. Clearly, however, not machine learning. That order page was not the least bit capable of reacting to an unfamiliar situation, and even the slightest change in the situation would have involved huge amounts of rewriting. You can think of the relationship between machine learning and artificial intelligence like this. Now, overall, you have the goal of providing intelligent responses to a situation, and you have multiple ways to do that. At the very outside, you have things like decision trees, like a giant if this, then that, or knowledge bases, or other rule-based decision making. Within that, you have machine learning, which is the ability to learn from situations and potentially generalize that knowledge so it can evaluate situations that haven't been seen before. So if you write software that gives you access to your files when you type in your password, that's artificial intelligence. Your password is a definite, recognizable piece of data. If you write software that gives you access to your files when it recognizes your face from your webcam, that's machine learning. That's because your face changes from second to second as you move. So it's not a fixed piece of data. But with training, the computer can recognize it. Now, you've probably also heard the term deep learning, which, as it happens, turns out to be a subset of machine learning. We'll talk about that later on. Now, machine learning uses a number of different techniques and algorithms, but at their heart, they all boil down to math, using things like probabilities and even geometry to figure out what one thing has to do with the other. But don't get scared. It's not going to be overly complicated, and in this unit, we're going to teach you all the math concepts you're going to need. Also, we're going to keep them in their own separate modules, so you can skip anything that's still fresh in your mind from math class. Now, there are three basic types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. Let's talk about those next. Perhaps the easiest kind of machine learning to wrap your head around is supervised learning. Supervised learning is what happens when you literally train the computer using existing data, which includes the quote-unquote right answers, and then the computer uses that guidance to make judgments on cases it hasn't seen before. For example, in my spare time, I'm starting to raise koi fish. Now, most of the time when you say koi, people think of what's basically giant goldfish. As it happens, though, there are dozens of different types of koi, and they all have different Japanese names. Now, I don't speak Japanese, so learning to identify all those different fish started out as something of a challenge, and before long, it started to feel more like this. But if I were going to actually sit down and find out what each of these fish are called, I'd eventually start to notice some patterns. Some types of markings have particular names, as do various colors. I can also see that if they have long flowing fins, then they're butterfly koi, and if they don't, they're standard koi. Now, in doing all that, I've used two features of the fish, their color and their fin shape, and I've learned what different values of those features mean. So eventually, I might look at a picture like this, and I'll be able to say, well, this one's a shirobeko, and this one's a kohaku, and this one's an ogon, and so on. Now, this is called supervised learning because I was trained with the right answers. And then I generalized that knowledge to the fish for which I didn't have any answers. Now, one nice thing about supervised learning is that we can evaluate how good it is. So, for example, if I wanted to know how good I was at deciding what the names of these fish are, I could keep out a set of pictures for which I have names and test myself to see if I get it right. Kind of like when you were a kid and you quizzed yourself before a test. If I get this validation set right, then I can have a good bit of confidence in what I'm calling the mystery fish. If not, then I either need to go back and train myself some more, or I need to train myself in a different way. Now, we don't have to think about how the human brain makes those decisions. It just does. But obviously, if we want to teach a computer to do the same thing, we need to be a bit more deliberate. And the method that we have the computer use is called the algorithm. For example, one way to look at it would be as a decision tree. I can make a decision about what kind of koi it is, like this. Now, that's pretty straightforward, if a little long, and it's pretty easy to imagine a computer doing that. In reality, though, these decisions are much more complicated. I mean, even the koi example looks more like this. And that it doesn't even take into consideration the fin shape or a lot of different specialties. So you can imagine it gets pretty complicated pretty quickly. Now, trying to code something like that manually is like that shopping cart example I talked about in the last module, where we had 3 types of phones and 3 different styles, And we just made a giant if-then statement to display the shopping cart. In this course, we're going to focus more on algorithms that let the computer learn things on its own in a more general way. For example, sticking with our fish, we might increase the probability that a certain word was going to show up in the name based on the specific color that appears on the fish. This would be similar to how a neural network processes different values to come up with a single answer. Now, that is, of course, a gross oversimplification, but the point I'm trying to make here is that supervised learning involves training the computer using existing knowledge that includes a right answer that we already have. Now, there are a ton of different supervised machine learning algorithms, and in this course, we're going to focus on linear regression, logistic regression, random forests, neural networks, and deep learning. We'll also touch on a couple of other techniques, such as support vector machines. Supervised learning is great for a lot of problems, but when you come down to it, it still creates machines that are only as smart as we teach them to be. With unsupervised learning, on the other hand, we're basically giving the computer a big pile of data and saying, here, see what you can make of this. Now, if we were to go back to our koi example, in that case, we'd just give the computer a bunch of pictures of the different kinds of fish or data about them, and it would group them together. Interestingly, it might not group them the way that we're expecting. For example, if we're naming the fish based on their color, we were naming the fish based on their color and their fin length. The algorithm, on the other hand, might group them by scale type or length or type of whiskers or even some other characteristic that we hadn't even noticed. The main thing is that the algorithm isn't constrained by our preconceived notions and can find relationships that we may miss, so it can process a lot of data. And frankly, that's a good thing, because there are some estimates that say that humans create 2.5 billion terabytes of data every single day. If that was carbon dioxide, we'd all be dead now. Now, there's no way that humans can sort through all that. So instead, we have machine learning algorithms that are designed to find commonalities and trends, like what drugs kill this kind of cancer, or what's the economic fallout of particular policies, or really important things like what are people talking about on Twitter. Some of the algorithms that can be used for this are k-means clustering, hierarchical clustering, Gaussian mixture models, self-organizing maps, hidden Markov models. We're going to mostly focus on k-means clustering in this class. Reinforcement learning is kind of a fun one because it brings together elements of both supervised and unsupervised learning. And because it's probably most like the way humans themselves learn. I mean, think about it. When you were a baby, you didn't know anything at all. So you tried stuff just to see what would happen. If you cried, chances are somebody stuck something delicious in your mouth or changed that wet thing you were sitting in. So you did more of that crying when you wanted those things to happen. Now, reinforcement learning is similar to that. The algorithm is designed to try and maximize a particular result or minimize some other result, combined with supervised or unsupervised learning. For example, researchers working on self-driving cars might train the system on what to do in specific conditions, like a straight road with nobody in front of it, or a stop sign, and have it run simulations with the goal of minimizing crashing into things. So that would be a combination of supervised learning and reinforcement learning. On the other hand, researchers created a machine learning version of the classic video game Pong and just gave it a goal of winning. They didn't teach it anything about the game, not even what the paddles look like. They just gave it a definition of winning and the ability to give up and down instructions. The algorithm then looked at the screen and analyzed what action to take based on the pixels themselves. So it learned that if the screen looked like this, and then like this, it needs to give up instructions to make the screen look like this. One great thing about reinforcement learning in gaming situations is that computers can basically play themselves. So they just keep getting better and better. Sometimes they even come up with techniques and strategies that experts hadn't even considered. One of the big breakthroughs in machine learning was last year when Google's AlphaGo program beat an expert player at Go, which is a game much, much harder than chess. In fact, the Korea Badok Association, which is sort of the governing body for the game in South Korea, awarded AlphaGo an honorary 9-dan, sort of a black belt in Go, I guess. Another example of reinforcement learning is Google searches. More and more, Google is using machine learning to decide which links to put at the top of the results. And then it measures how many people click on those links to determine whether it made the right decision or not. We're not going to talk much about reinforcement learning itself in this course, but of course you need to have the background for the learning part if you're going to try it, and that's what we're going to work on. Okay, so conceptually, that's what we're talking about. Now, let's get on with the math. Before we get into the math, I'm going to make a confession to you. I went to college to be a physicist. Not that that's anything to be ashamed of course, but I think it's important to tell you that I wound up switching over to be a high school physics teacher. Why? Because I didn't like how it seemed that the universe was being defined by this complex math that always seemed to be whizzing just over my head. So I decided to go back to a level where the math just made intuitive sense. Why am I telling you this? I'm telling you this because I want you to realize that I am not a mathematical genius. When it comes to these topics that might seem like they're going to be overly difficult, if I can do this, you can do this. Now, I've said that we're going to get by with some fairly basic math, but it's important that you're pretty solid with the concepts that we do use. So before we get started, I'm going to cover the slope of a line and what it means, how slopes work with curved lines, scalars, vectors, and tensors and what they are, and the basics of matrices and how to do math with them. Now, if you're coming out of school and all of these things are second nature to you, you feel free to skip ahead to the next section. But for the rest of us, we're going to take just a few minutes and make sure we've got our footing. Let's start with slopes. Now, this may sound like a real oversimplification, but when you come right down to it, finding the slope of a line is pretty much the bedrock of the vast majority of machine learning. So let's get down to it. Let's say that we drive from, say, Charlotte, North Carolina to Cleveland, Ohio, and we want to graph the distance traveled based on the time it's taken. Let's also assume that we really weren't paying attention during the trip, so all we know is when we started and when we ended up. So we might wind up with a graph something like this. Now, if I were to ask you what the average speed for the trip was, even if you don't know the formula, you might say, okay, speed is in miles per hour, and we went 500 miles, and it took 10 hours, so that's 50 miles an hour. And that's right, of course. And it's intuitively the way to find the slope of a line. By definition, the slope of a line is called the rise over the run, or the change in x, or the change in y over the change in x, or delta x. So in this case, we had 500 miles over 10 hours. If we took a smaller piece of the graph, we could see that it works out the same way. Now, because this is a straight line, any section that we pick is going to have the same slope. Now, if we were going to try and figure out approximately where we were at any given time, we would say, all right, distance equals 50 miles an hour times the number of hours. So 2 hours after we'd left home, we'd have gone about 100 miles. If we were to turn this into an equation for the line, we would say y equals mx, where m is the slope of the line, or in this case, 50. Now, let's say that we left too late in the day and we only made it to Wytheville, Virginia before we had to stop for the night. If we were to graph the distance from home during the next day, we'd have to note the fact that we're starting the day with 140 miles already under our belt. So if we wanted to figure out how far we'd gone during day 2, we'd have to say distance equals 50 miles an hour times the number of hours plus 140 miles. In this case, 140 is what's called the y-intercept, because that's where the line intercepts the y-axis. If we were to turn it into an equation for a line, we'd have to say, okay, y equals 50x plus 140. If we were to look, we'd say, all right, after 2 hours, we'd know that we had a total distance of 240 miles. So that would be what's called y equals mx plus b, where b is the y-intercept. And just to be clear, that works when we have lines that go in the other direction too. So for example, if we were tracking the amount of traveling we'd have left to do, that would be a negative slope because we'd have an equation of distance left equals 500 miles minus 50 miles an hour times the number of hours, or more properly, minus 50 miles an hour plus times the number of hours plus 500 miles. In this case, we still have y equals mx plus b, but m equals minus 50 and b equals 500. Okay, so that's what happens with a straight line. But what happens if it's not straight? What happens if we were actually trying to find the slope of a curve? For example, if we were actually paying attention when we were graphing how far we'd gone on that drive, we might have something more like this. So we might make some good time on the highway, but maybe we ran into some traffic here, and maybe we got off the highway and took some back roads for a while before we got back on the highway. Okay, so unlike in our last example where the speed and therefore the slope was a constant, in this example the speed is going to depend on what section of the trip we're looking at. For example, if we look at this section, we can see that the slope is 130 over 2, or 65. On the other hand, this section over here is only 30 over 1, or 30. But what do we do with sections like this where there's a curve? Well, if we look at a smaller section, we can get a rough idea of the average speed during that time period. And if we shrink that time down even more, we get a more precise speed, but it's still an average. If we keep shrinking it down until we're looking at a single point, there's a sort of instantaneous slope called the tangent. We can also figure this out by taking the derivative of y with respect to x, but we're not going to go into the actual derivations of any of this stuff, so don't worry about that. The important thing to understand here is that even though this is a curve, there's still a slope in the form of y equals mx plus b. Now, in this example, we've been talking about speed, which some people think is the same thing as velocity, but it's not. One is a scalar, which means it just has magnitude or length, basically, and one is a vector, which means it has both magnitude and direction. In the next section, we're going to talk about what that means and why it matters. So, as I was saying at the end of the last module, speed is a scalar and velocity is a vector. But what does that actually mean? Well, for one thing, it means that if I ask you the velocity of a car that travels 500 miles from Charlotte to Cleveland in 10 hours and you say 50 miles per hour, you're wrong. The actual answer is 50 miles an hour northward. Well, more or less northward, but you get the point. The vector has magnitude, in this case 50 miles an hour, and a direction, northward. Basically, a scalar is a point, while a vector is a line with a specific direction. So a scalar is zero-dimensional and a vector is one-dimensional. But let's make sure we've got this here. We're talking about just the line here. So this is a vector. And this is a vector. And this is also a vector. The important thing is that in all of these cases, we're only talking about the points along the line. So even if we're defining the direction along multiple axes, it's still a vector. We can even define a vector with more than 3 components, but I can't draw a picture of it because we live in 3D space. So, okay, why do we care about all this? We care because in machine learning, a good bit of the data that we're dealing with is going to have multiple features or components. So it's going to act like vectors or their higher order cousins, which we'll get to in a minute. Now, notationally, we write a vector like this. So if we have a vector like this, it looks like this. The magnitude, or the length, basically, is c squared equals a squared plus b squared. It's just the Pythagorean theorem, like in high school. If we want to make this a unit vector, or a vector with magnitude of 1, we divide the sides, or the components, by the length, like this. So it still points in the same direction, but it's shorter. Specifically, it has a length of 1. Okay, so a little vector arithmetic. We can add vectors. So if we take the vector 6, 4, and then we want to add the vector 2, 6, we do that by adding the tail of the second vector to the head of the first vector. And that makes sense. Because think about it. If you go 50 miles north and then you go 30 miles east, you don't go back to the beginning first. You just start where you are. So at the end, we wind up adding up the dotted lines or the components of the two vectors. We can also multiply a vector by a scalar. Let's say we start with the vector 4, 2, and we want to multiply it by 3. Well, just like in grade school, multiplication is adding things multiple times. So we have the same vector 3 times, which is the same as multiplying each of the components by the scalar. And by the way, when we put things in parentheses like that, it just means that we're multiplying. Now, that's the same as when we made it a unit vector, but in the other direction. We can even multiply a vector by a vector. We can take what's called the inner product like this. I know this is a little bit of weird notation, but we're going to talk more about it later. The important thing here is that we figure this out by multiplying the components and then adding them up. So again, we'll give a bit more of an example later, but the end result in this case would be 20. All right, so a scalar is represented by a single number and a vector is represented by a group of numbers. If we have a group of vectors, that's a tensor. So you might have a tensor that's represented by a matrix of numbers like this. We'll deal with matrices in a minute, but first, if we put scalars together to make a vector and we put vectors together to make a tensor, what happens when we put tensors together? Well, actually we get another tensor. In fact, scalars and vectors are just special kinds of tensors. A vector has one set of coordinates, so it's just a first order tensor. A scalar has none, so it's a zero order tensor. This is a second order tensor. This would be a third order tensor. And so on. But I think if I tried to show it, I would sprain my brain. So this is just a special case of this. Fortunately, dealing with tensors and the matrices that represent them isn't as complicated as it seems. You can think of a matrix as a grid of numbers like this. Matrices are basically tables of numbers. For example, we might have a set of data like this. The features or properties are all important, and they're important over multiple measurements. So one way to represent all this information might be a matrix like this, where each row of data is a row of the matrix. So how do we deal with this kind of thing mathematically? Fortunately, we've actually seen almost all of the pieces that we need already. For example, we can add two matrices by adding the corresponding components like so. If you remember, that's just like what we did with the vectors, but now in 2 dimensions. We can multiply by scalars the same way, too. But what about multiplication? That's got to be a little more complicated, right? Well, yes and no. In fact, you've already done it. Remember when we multiplied the vectors? In this case, we were actually doing a matrix multiplication, just with very small matrices. Let me show you what I mean. We can write these two vectors as matrices. And then to take the inner product, we're going to take what's called the transpose of the first one. So our inner product was actually multiplying the transpose of one matrix by the other. The dot is a symbol for multiplication. Now, you may be saying, that's silly. If we were going to multiply them together like that, why didn't we just leave them both vertical? Well, the reason is that it's not always that simple. Okay, so now what do? Fortunately, we do more of what we already know. We start with the first row and the first column. Just as before, then we do the first row and the second column, and then the third, and so on and so forth. Do the second row. That's the second row. So you'll notice something here. These two sizes have to be the same, or you can't do the multiplication. Now, this is important because we're ultimately going to use it to do things like multiplying this image by this matrix of probabilities. But that's for later. Right now, rejoice in the fact that that's all the math you're going to need for this course. Now let's get your computing environment set up so that you can do machine learning. So before we go any further, let's go ahead and set up your environment. We're going to be using TensorFlow with Python, so we want to create an environment something like this. As you can see, we're assuming that you're using Ubuntu, specifically Ubuntu 16.04. So if you're running on some other operating system like Windows or Mac, that's fine. It's not a problem. What you can do to follow these same instructions is to set up a virtual machine, sort of a computer within a computer, and make sure that it's running Ubuntu. And you can do that by downloading Oracle VirtualBox at virtualbox.org. You can find all the installation instructions there. Once you've done that, go ahead and create the Ubuntu VM, and then you can just follow the same instructions we're using for the rest of this. Now, we're going to use a scripting language called Python for this course for a few different reasons. First, it's pretty easy to learn, at least to get proficient enough to do basic tasks. And that's probably part of the reason it's really popular these days. And that leads to the second reason we're going to use Python, which is that all of the tools we're going to use, such as TensorFlow and scikit-learn, have great support for it. Now, Python is weird because it's actually not backward or forward compatible. And what I mean by that is that while you'd expect some things from Python 3 not to work in Python 2, Python 3 was such a rewrite of the language that there are structures in Python 2 that won't work in Python 3. I'm bringing it up because it means that we need to make a hard choice. So because we're looking forward to the future here, we're going to go ahead and use Python 3. But we're not going to do anything super sophisticated or anything, so you're not going to learn anything here that you can't take back to your Python 2 environment, as long as you're willing to go ahead and make some minor syntax fixes. Okay, so with Ubuntu 16.04, we don't actually have to install Python 3 at all. It comes installed by default. We do, however, need to get some tools that we'll be using with Python. We'll start with pip, which is a Python package installation tool. And then we'll go ahead and we'll install it. So first we download it, and then we run it to do that. So once you've got that, you can execute sudo python 3 get pip py to install it. Once we have pip installed, that's going to make installing everything else much easier. Except one piece we need, which is matplotlib. So let's go ahead and install it. We'll be using that for printing out plots and graphs and such to make things easier. So fortunately, you can just use regular Ubuntu installation tools to go ahead and install that. Now, creating a virtual env environment is not strictly necessary. And in fact, I resisted doing this for a really long time, but trust me, it is worth it. Virtual env lets you create an environment that's independent of the rest of your machine. So you won't have problems with conflicting libraries. And believe me, when you're trying to figure out why something isn't working, it is great to be able to rule that out right away. So what we want to do here is install the virtual env software and then create an environment to work in. First, we'll use pip3, which we installed earlier, to go ahead and install it. So we'll just run pip3 install with the upgrade virtual env. And then we'll tell virtualenv to go ahead and create the actual environment we're going to use. Now, the name itself is arbitrary, so I'm just going to call mine tensorflow. We're using site packages so that we kind of inherit everything that is already there. So we're going to include the packages that exist on the machine as a whole. Now, I feel safe doing this because this is a fresh VM for me. But if you have any concerns, you can skip that and just install packages as they come up. OK, so now we have an environment created. So to access it, we want to go ahead and activate it, which we'll do by sourcing the activate file. So we have our environment, and we can go ahead and install TensorFlow itself. OK, so we have our TensorFlow environment, but that's just an arbitrary name. I could have called it Bob. Just creating an environment called TensorFlow doesn't mean that TensorFlow is actually installed. Fortunately, installing it should be as easy as using pip again. So we're going to just, do another install using pip. Now, this should work, but TensorFlow is an ever-changing beast. So you might find that you have to download specific files and install manually. But if you do, there are pretty good instructions on the TensorFlow site at tensorflow.org. All right, so now it's installed, and we can go ahead and make sure it's working. To do that, we're going to create a very simple file that uses TensorFlow. So start by creating a new file by typing vi hello tensorflow.py. For those of you who haven't used VI before, a couple of simple commands. To insert, press the I key on your keyboard. If you want to use something else, that's fine. There's no reason that you have to use VI. But for these instructions, I'm going to show VI. So now we can go ahead and put in our code. If you already know Python, please bear with me as we take a few minutes to orient people who maybe haven't seen it before while we give you the basic mechanics of how TensorFlow works. TensorFlow runs better on a graphics processing unit, but since we haven't installed it that way, we're going to turn off the messages telling us about it. You don't need to worry about understanding this code. We'll just copy and paste it here at the top of each file. It's just setting the error level so we don't get those messages. All right, now we're going to tell Python 3 that we want to use TensorFlow by importing it and giving it an alias tf. That means that when we refer to it in the script, we can just say tf. So we have import TensorFlow as tf. TensorFlow has its own variables, constants, and so on. So we're going to create one here just to make sure everything is working. So as you can see, we're creating a Python variable message, and we're assigning it the value of a TensorFlow constant that's set to a string. It says, hooray, TensorFlow is working. And then we'll print that out with the print command. This is pretty simple. So message equals tf.constant, and then we're setting the value of the constant. Remember, it's just a function. And then we're printing the message. OK, so let's stop here. Press the escape key on your keyboard to come out of insert mode. And now to save this, we want to type a colon. And when you do that, you'll see that you get a cursor at the bottom. And then you want to hit a lowercase w for write and hit enter. So to go back to the command line, you can type :q. Now, before we do anything else, what do you think this program's going to output? I mean, it makes sense that it would be, hooray, TensorFlow is working, right? Well, let's see. All right, so now to execute this file, we want to have Python run it. So we'll type Python 3 hello tensorflow.py. Well, that's not pretty, and it's not what we expected at all. But it shows you that these TensorFlow objects, such as constants and variables and things, they're just constructs until we tell TensorFlow to actually do something with them. So let's go ahead and do that. To get back into our file, we'll type vi hello tensorflow.py again. And you can see that it brings us right back to where we were. You can use your arrow keys to get to the bottom of the file, and then type the A key to append more code. Now, in order to make TensorFlow do anything, we need to create a session, which is where the work will be done, and then we'll go ahead and do that, and then we'll assign it to the session variable so we can work with it. So session equals tf.session. Again, right now, message is just an empty object. So let's run it to make it meaningful. And when we do that, we can assign its value to a variable, which we're calling output. Now, by default, this is going to be what's called bytecode. So we want to pretty it up a little bit. To do that, we're going to tell the output variable to use its decode function to convert it to a string, and then we're going to go ahead and print it out. Okay, now let's go ahead and press escape, and we can do :WQ to save and quit in one step, and then we'll run this again. So we've got Python 3, hello tensorflow.py, and there we get the original code, and also, hooray, TensorFlow is working, which is what we want to hear. Okay, now, if you got an error, you should also see a line number about telling you where the error happened and some indication of what went wrong. So you can go back and fix it as many times as you need to make it work. All right, so now we're all set to go. But before we do, let's take a quick minute and talk about the projects that we're going to do in this course. So the great thing about machine learning is that it's not just for PhDs anymore. In fact, anybody can do it, given the right circumstances and the right training data. So in this course, we're going to do a number of different projects. Like I said, we're not going to build any self-aware robots or anything, but we are going to do a few things that will give you an idea of how machine learning is actually being used today. We'll start with predicting article popularity. I'm sure that you've noticed there's a heck of a lot of content out there, and frankly, it's just getting worse. So if you're a content creator, and most of us are, whether we like it or not, you really want to know what's working and what's not working, preferably before you spend a lot of time on it. We're going to take a large data set showing how various Mashable articles did on social media and use it to determine what factors are most important for predicting success. Next, we'll take the classic spam filter. There's a ton of different ways to do this, but we're going to make a simple classifier that learns from your existing mailbox and classifies email as spam, ham, or steak, which would be the emails that you want to pay particular attention to. Then we're going to use unsupervised learning to look at determining trends and sentiment analysis in social media. There are a ton of applications from this, for businesses that just want to figure out if people like them or trying to determine what's the next big thing coming down the line. And then finally, we're going to build a neural network. Yes, I promised you we would. And we're going to use deep learning to do the classic handwriting recognition project using images. Okay, you ready? All right, we'll see you in Unit 2.
Okay. Now that we're all set up, we can start looking at actual machine learning tasks. We're going to start simple with supervised learning and linear regression. Now, if you remember, supervised learning is when we have data that is already labeled and we train the algorithm using that data. Once it's trained, it can then predict labels on data it hasn't seen before. For example, in this unit, we're going to use a data set of analytics from the website Mashable, which, if you haven't been there, is a tech and entertainment website with something like 50 million visits a month, so the sample size is pretty substantial. Each one of these records includes information about one article from the Mashable site, including the URL, when it was published, how long the article was, how many keywords it targeted, what day of the week it was, and so on and so on and so on. Each one of these facts about the article is called a feature. We're going to start out with a simplified version of the data that looks like this. As you can see, this data has 4 features: the URL, the title length, article length, and the number of keywords. It also has one label, the number of shares. The difference between a feature and a label is that the feature is measured, while the label is what you're ultimately trying to predict. Ultimately, our goal is to define a mathematical equation that relates the feature to the label so that we can use it to predict unknown labels using just the features. Think of it like a recipe. If you know that you have 12 goats and they eat 24 cups of feed a day plus 3 flakes of hay, if I told you that I was feeding 48 cups of feed a day as well as 6 flakes, could you tell me how many goats I was feeding? Sure you could. Simple algebra. 12 goats equals 24 cups of feed plus 3 flakes of hay. So if we divide both sides by 12, we see that 1 goat is 2 cups of feed and a quarter flake of hay. So you know that if you have 48 cups of feed and 6 flakes of hay, you can predict that you are feeding 24 goats. The key here is in using your data to figure out what the recipe is so that you can make those predictions. In the next module, we're going to look at trend lines and what they have to do with those formulas. In Unit 1, we talked a lot about the slope of a line, and there's a good reason for that. It's because when we're trying to find those formulas, we do it by finding a line that best fits the data that we have. You can think of this line of best fit as the trend line. Let's say we're going to order some paper clips with flat rate shipping. We can plot what the order will cost us on a graph. These points are all on a line, so we can easily draw that line. This makes it really easy to find the formula of the line because we can just take 2 points and find the slope, as in slope equals the rise over the run, which is 14 minus 8 over 3 minus 1, or 6 over 2, or 3. So we have a slope of 3. And then we can find the y-intercept, which remember is where x equals 0, by using the formula y equals mx plus b. So if we take one of those points, 1, 8, we start out with y equals 3x plus b, and then we have 8 equals 3 times 1 plus b, or 8 minus 3 equals b equals 5. So the equation of the line is y equals 3x plus 5. You can think of that slope, the m, as the weight. For example, in this case, for every box of paper clips you put in your shopping cart, it's going to cost you $3. That's the weight of the paper clips. The y-intercept, on the other hand, is the bias. That's the number you're going to pay regardless of how many boxes of paper clips you buy, or in this case, $5. The idea of weights may make a little bit more sense if we look at more than one feature. For example, if we were trying to find the price based on the number of paper clips we're buying and the number of steaks we're buying, we might find that the price increases based on the steaks much more strongly than on the paper clips. In other words, the steaks have more weight. In math terms, this might become price equals the weight of the paper clips times the number of paper clips plus the weight of the steaks times the number of steaks plus the bias, which is the shipping. In this case, we're changing what we call the slope, but don't get confused here. That's all it is. It's just a generalization of y equals mx plus b. Okay, so we started with an example where all of our data points are on the same line. But what if they're not? What if it was more like this? Well, we can still make a line that best fits the data. We just have to work a little harder. So in the next module, we're going to look at cost functions and the graphs they make. We're trying to find a straight line that best fits the data that we have, but in order to do that, we need to define what we mean by best fit. For example, if we have a set of data like this, we can have any number of lines that approximate that data. But which one is the best? In this case, we're going to define best as the line that has the lowest cost. Now, the cost function is a measurement of how far off the line actually is. For example, we can measure the cost by measuring the distance of each point from the line, then adding that up. So if we have 5 points here, the cost in this case would be the sum of these green lines, which are the difference between the actual value and the point on the line, which is the predicted value. There are other ways to do this, but we're going to keep it simple. In fact, we could make a formula out of this. We could say the cost equals the sum of the absolute value of y minus the predicted y. In order to make sure we always get a positive value for the difference between the actual and predicted values, one common thing we do is to square the difference, as in the cost equals the sum of the square of y minus y predicted. We call that the cost function. So we can evaluate how close each line is by plugging it into this formula. You'll notice that these weights are very important in determining the value of the cost function for a particular line because they determine the value of y predicted. So Because the cost basically measures the difference between the actual and predicted values, it stands to reason that the line that approximates the data the best is going to be the line with the lowest amount of that cost. To figure out what that is, we need to figure out what the least cost, or the minimum, is, and what weights are going to make the cost function give us that minimum. We're going to do that using a technique called gradient descent. Gradient descent is quite possibly the most important thing you can learn about when it comes to machine learning. It's a really important foundation underpinning a very large percentage of what you're going to do. So let's look at it on a conceptual level before we look at the math. Have you ever played a game of hot or cold? This is a game where one person decides what the other one's looking for and gives them clues. If they move closer to the object, they're getting warmer. If they move farther away, they're getting colder. So if you're the seeker and you know you're getting warmer, you keep moving in that direction. If you're getting colder, you turn around and go in the other direction until you're told you're getting warmer again. That's what's called a qualitative way of looking at solving the problem of finding an object. It gives you the general idea, but it's not specific. You can't really measure it. Another way to look at it is quantitatively. Let's say I told you that I was thinking of a number between 1 and 100, and I wanted you to guess what it was. After each guess, I would tell you whether you were too high or too low. It's kind of like hot or cold, but you can be more deliberate here. Now, 100 sounds like a pretty big range, but chances are the conversation would go something like this. So, with only 4 guesses, Sarah managed to figure out what number I was thinking of, even though it was pretty far to one extreme. Gradient descent works a lot like this. You make a series of guesses, and with each guess, you're trying to get closer to the actual value that you want. You're trying to decrease the cost, or the loss function. Now, if the number I was thinking of was 83 rather than 82, it might have taken a few more iterations to get to the right answer. But what's important here is that after every guess, Sarah knew which direction she needed to go in, so she would have eventually gotten there. In this case, if we were to graph the cost function, or the amount by which each guess is off, it'd be a pretty simple graph. There's an interesting trend in this function. On the left side, the slope is negative. In other words, the cost is decreasing as we move closer to the right answer. And on the right side, the slope is positive because the cost is increasing as we move away from the right answer. Right in the middle, at 82, the slope is 0. That's called the minimum of the cost function. That's what we're looking for, and by knowing the slope of the cost function at any particular point, we know if we're moving toward the right answer or away from it. Now, that's a really simple example, and because all the lines are straight, it's pretty simple to see exactly where the minimum is. But let's say we wanted to generalize this and figure out article shares based on article length using the simplified Mashable data. In this case, our cost function is based on the distance of each point from the line, but because we want it to always be positive, we'll square it. Remember, when you multiply a negative by a negative, you get a positive. So in this case, the shape of the line looks more like this. All right, now this is a really big simplification, but go with me here for a minute. Got a nice parabola there, and we want to find that bottom point where the cost function is literally at its lowest. Now, think of this as a ski slope, and this is a valley. Let's say you broke your skis and you wanted to get into the valley. You wouldn't go uphill, right? No, you'd want to find the path that took you downhill the steepest. Well, ignoring the possibility of falling down the mountain and breaking your neck and all that. It's a hypothetical mountain. In this case, it's pretty easy to see, but it works in 3 dimensions too. Here you'd want to find the direction of steepest descent and take that. And the size of your steps is something that you'd decide. Are you going to take large steps or small ones? At the beginning, probably large steps. Like when Sarah chose 50 in the guess our number example, she was right in the middle. It was the biggest step she could take. But as you get closer, you'll want to choose smaller steps. This choice is really important though, because if you choose a step that's too large, you might jump over to the next mountain. But if you choose a step that's too small, you might freeze to death before you get to the bottom. Okay, so that's the general idea. In the rest of this unit, we're going to see how exactly we make this all work. But before that, we need to know how to make all this data visible. We're going to do that with a tool called matplotlib. Before we start manipulating data, it's important to understand how we're going to visualize it. And to do that, we're going to use a tool called matplotlib. Now, matplotlib is a Python-based graphic program that makes it really easy to create graphs and charts, as well as images, out of data. In fact, I've been using it for all the graphs and diagrams in this unit, and it has made my life a whole lot easier than trying to draw them by hand. It lets you draw 2D and 3D diagrams, and it even does animations. So, why is this important? It's important for the same reason that speedometers have gauges with needles instead of just numbers. Can you imagine flying down the highway at 70 miles an hour and having to interpret this? No, it's much faster and much more efficient for your brain to see this. So, the same thing applies for data. For example, if I said to you, what are global attitudes about corruption organized by country and institution? Would you rather use this or this? I'm assuming you'd rather use the visualization. Would you rather look at tables of ocean current data or look at a video like this? Okay, so let's look at how to do that. Now, I can't draw my way out of a wet paper bag with lighted exit signs, so I'm not going to be showing you how to do these beautiful visualizations, but I can definitely show you how to make some graphs and charts, and you can take it from there. So the data we're going to use looks like this. Now what you see here is 100 data points. Each of them has 4 aspects or features that tell you something about that piece of data. For example, this one has a URL of mashable.com and the date and HTC-Q1. That's one feature. Another feature is the length of the title, which is 2 words. Another is the length of the article itself, or 364 words. The fourth one is the number of keywords we're trying to hit, which in this case is 4. The last item is the value that we're trying to predict, which is called the label. In the case of this data set, the label is the number of shares the article got, or 456. We're doing supervised learning here, so the idea is to find the relationship between the features and the labels. So if all we have is features, we can predict the unknown labels. Let's start by creating a graph that shows the relationship between the length of the article and the number of shares it gets. So the first thing we're going to do is go ahead and create a new file for our Python script. Again, use any editor you want. I'm going to use VI. I'll start out creating a new file called graphing.py. Now, the first thing we need to do is import 2 packages. One is matplotlib, which is a Python plotting library, and specifically the pyplot package from matplotlib. If you don't have matplotlib installed, go back to Unit 1 and install it, and then come back. I'll wait. So we're telling Python that we want that package and that we're going to give it an alias of PLT so we don't have to write matplotlib.pyplot every time we want to do something. So that's one package. The other is NumPy. Now, NumPy is one of the most useful packages you are ever going to use in Python machine learning applications, and maybe in Python altogether, depending on what you're doing. It enables you to easily import and export data and to manipulate it in a way that's really similar to database tables. So we're going to go ahead and import that and give it an alias of NP. Okay, so next we're going to go ahead and read in the data. We've got it in a file of comma-separated values, or a CSV file. So the first thing we need to do is to define the names of each of these columns so we can reference the data by name later. So briefly, for those new to Python, we're creating a variable, columns, and we're assigning it a list of the different column names in the order in which they appear in the file. Okay, once we've defined the names, we can go ahead and create a variable to hold the data. And then we'll tell NumPy to generate what's called an array of data from the text. So we've got np.genFromText, and then we feed it the name of the file, which we have right here in the same directory, and we specify the delimiter, or the character that breaks up the columns, as a comma, and we tell it what the name of each column is by feeding it that list we created a minute ago. Now, just a quick note here. Yes, there are other ways of doing this using other packages, but we're using NumPy right now, so this is what we're doing. Now, let's make sure it's working by printing out the number of items in the file. We're going to say print, of course, and then we want the length of the data array, so we're going to say len data. Now let's save the file, and we can run it by typing python3 graphing.py. So as you can see, it reads the file and tells us that there are 100 lines in it, which we already knew, but it is kind of cryptic, so let's make it a little nicer. So we'll open the file back up, and what we're going to do here is we're going to make a string of characters that says there are X number of items in the array. You'll notice that we're adding these strings together using a plain old plus sign. Now, Python knows how to add integers, and it knows how to add strings. But it'll get really confused if we try to add a string and an integer together. So we'll make sure that we tell it that we want to treat that length like a string using the string function. There are other ways to combine things for printing, and we will talk about them later. But for now, we're going to keep it simple. So now if we save it and run it, we can see it's a little more user-friendly. Now, before we move on to actually creating the graph, let's just make sure we know what the array looks like. Basically, it's a structure like this. It's essentially an array of arrays. Each row in the document is an array, and we have an array of rows. You'll notice that the URL has been replaced with this nan notation. We'll talk about that later. One thing that we can do is we can print out a single row, like this. So this would actually be the 43rd row, since it's a zero-based index. Another thing we can do, though, is to print out one column, so to speak, like this. Now, what we've done here is we've created a list that consists of just the article length values. And this is important because there will be times when we want to act on just that data. Okay, so now let's look at how to visualize all that data we just read. The first thing that we do is tell PyPlot to create a new figure. What we want is ultimately something that looks like this. So we'll start by creating a figure. Remember, we created an alias of plt for pyplot, so this is the same thing as typing fig equals matplotlib.pyplot.figure, but let's stick with the alias. So we have fig equals plt.figure. Next, we can label the two axes. We want the x-axis to represent the number of words in the title, and the y-axis to be the number of shares, so we can literally just set those labels. Now, if we want to see anything, we have to tell PyPlot to show the figure. Great, so that's something. Now we just want to go ahead and add our data. So we'll go back to the script, and in this case, we want to do a scatter plot where each point is represented by the length of the title and the number of shares. So we'll use the scatter method or command before we do the show. Here you can see we're specifying all the title length values as X and all the shares values as Y. Because these are two lists, they'll match up. So the first X goes with the first Y, and the second X goes with the second Y, and so on and so on and so on. Now, we're also specifying that we want the color to be red. So we'll say R. We could use G for green, B for blue, and so on. And we're setting the scale, or the size, to be 5. Now, notice that we're not putting quotation marks around that 5.0, which may be confusing for some people. But it's a real number. It's not a string, so we're just including it straight like that. Let's see what we have now. Great. So as you can see, we have points for each of these values, though there doesn't seem to be too much rhyme or reason to them. Let's go ahead and compare the other features and see if we can make any more sense of it. So the first thing is to go ahead and specify that our first figure is not the only one by giving it a number. And we can go ahead and add a second figure for the article length. Now, notice that it's all the same, except that we're using the article length rather than the title length. Finally, we'll add a third figure to look at the keywords. Again, it's all the same, except we're using keywords. All right, now let's go ahead and run it. As you can see, we specified 3 figures, and we got 3 separate figures. And if we look at each of them, we can see that the article length seems to have the strongest correlation with the number of shares, though there seems to be some relationship for all of them. It's always good to do some primary analysis to see where you're coming from, so you're not just shooting in the dark. In our case, we'll try to find the exact relationship between the article length and the shares. We'll do that in the next module. Now that we know how to read and visualize the data, let's go ahead and actually analyze it. As you remember, in the last module, we were looking at showing the relationship between the features of an article, such as the article length and the number of shares, or the label. In this module, we're going to take that information and use it to predict the number of shares based on just the article length. Now, what we want to do is find the line that best fits this data so that we can predict the number of shares based on the length of the article, so we know how long to make our articles to get the best uptake. We know that it's going to look something like this. We just don't know what the actual equation is yet. Now, remember, the equation for a line is y equals mx plus b, or in machine learning vernacular, y equals w times x, where w is the weight. Or in this case, shares equals w times article length plus b. So we want to write a script that'll get TensorFlow to tell us what w and b are, so that we can predict the number of shares. Let's start by creating a new file called predict_shares.py. Now, before we jump into the code, let's look at what it is we're actually trying to do. We're essentially going to do 6 steps. We're going to load the data, just like we did for the last example. We're going to define the predicted model, which is what we think the equation for the data will look like. We're going to set up the variables. TensorFlow is going to do all the work, but we need to give it the appropriate pieces to work with. We're going to define the loss and the optimizer. I mean, we know we want to minimize the errors between the predicted data and the real data, so we need to define how we're going to represent that loss and how we're going to optimize that. Then we're going to run the algorithm. Once we have everything defined, we can actually run it. And then we're just going to show the results. Okay, so let's look at the actual code. We'll start by suppressing the GPU warning. Now let's go ahead and import the packages we need. The first two should look really familiar from the last module. And then we're importing TensorFlow and giving it an alias of TF. If you jumped ahead and you haven't installed TensorFlow yet, go back to Unit 1 and take care of that before you move on. Okay, so next we're going to go ahead and read in the data just like we did in the previous modules when we were just displaying it. We'll set the list of column names, and then we'll read the CSV file and put the data into a variable. Okay, now we actually get into using TensorFlow. We'll start by setting up the initial variables and placeholders. So let's start by creating the weights. Remember, we're trying to... And if we translate that into the data we're dealing with, that'd be y equals shares, m equals weight 1, x equals article length, and b equals weight 0. So shares equals weight 1 times the article length plus weight 0. Now, why did we turn m and b into weights? Well, we did it for a couple of reasons. First, because later when we're dealing with other algorithms, it's going to be way more intuitive. Second, we did it because when you come right down to it, this really is just a small version of a bigger problem. Later, when we look at an equation that's more like this, you see here how the number or index for each weight corresponds to the exponent for x? Convenient, right? Well, in this case, we're just dealing with these last two terms. So y equals weight 1 times x plus weight 0. So in this code, it's going to look like this. Notice that we're defining w as a TensorFlow variable, which means that while we're defining it and giving it a value, it's really just an object until we actually execute the algorithm. We can tell that if we print out these values and then run the script. So let's go print it, and then we'll run it. So basically, we're just creating this structure for TensorFlow to use later. It's the same thing for creating placeholders for the shares and the article length. Now, let me just say it is really easy to confuse placeholders and variables, especially because when we first learn about variables, we're usually told to think of them as placeholders for the value. But in this case, we're talking about actual TensorFlow placeholders, and they're special. You'll notice we didn't actually set a value for these. We just told Python that they're TensorFlow placeholders, and they're going to take float values. Those are basically decimal numbers. What we're going to do with those is add them to equations so that when TensorFlow runs the algorithm, it knows where to put the data. Now we can go ahead and define our prediction. By the way, that'll work, but if we wanted to, we could also go ahead and use TensorFlow's functions to do that. There's no real reason to do it right now, but later we're going to see that there are other functions that TensorFlow gives us. Okay, so now we're ready to go ahead and look at the loss function. That's the measure of the difference between what the algorithm thinks the answer will be and what it actually is. But we're going to square it so it's always positive. We want to find the values that are going to make this loss as small as possible. Now remember, shares and predicted shares don't actually have any values yet. We're just creating those structures that TensorFlow is going to evaluate when the time comes. Okay, so now we define the error, and our goal is to minimize that, and we're going to do that using the gradient descent optimizer. We talked about the idea behind gradient descent in the previous module, so if you need a refresher, go on back and look at that. What we're doing here is defining the step size and telling TensorFlow that when we run the optimizer, we want it to minimize the error, taking steps of, in this case, 0.0015. Finally, we can define the model as the collection of variables. Okay, so now that we've defined everything, we can actually run the algorithm. Okay, so now that we've defined everything, we can actually run the algorithm. To do that, we're going to create a session. We'll start by running the model to initialize all the variables. Then we'll actually run the optimizer. To do that, we'll run it with the session, just as we did with the model, but in this case, we're feeding it the data to use. The data is an object with two named members, article length and shares, and each of them is a list of values. But those names, article length and shares, they sound familiar. Yep, those are the placeholders we created earlier. So we feed the optimizer those values, and the optimizer propagates the values through to all of the equations that flow from that. And because we define the weights as a TensorFlow variable, TensorFlow goes ahead and updates their values as part of this process. So if we go ahead and get those values, we can go ahead and print them out. Now, I know that print statement looks a little nutty, but basically we're just substituting formatted versions of A and B into the string. This lets us define them both as floating point numbers, hence the F, with 3 decimal places. All right, so let's go ahead and run this. Great. So it all works. We started out with our weights both being 1, and now there's 65.986 and minus 0.656. Of course, that's not very accurate. We can tell that if we graph the results, which we can do just as we did in the last module. So we're creating the figure and we're showing the raw data, but then I've added a plot command that'll create a smooth line that represents the predicted data. We're using the article length as X, and then we're calculating Y based on the model we've defined. So if we run this, well, it works, but it's terrible. And of course it's terrible. It's like guessing a number between 1 and 1,000,000, but only taking one guess. So to make it better, we'll make a series of guesses, with each one presumably getting better. So we'll tell it to take 100,000 guesses. And of course that's going to take a little while, so we want to print out the values periodically. In this case, we'll do it every 100 steps. For those of you new to Python, this notation means you divide I by 100, and if the remainder equals 0, we execute the print statement. Okay, so now if we run it, wait a minute, nan? What the heck is nan? Okay, so nan in this case means not a number. More specifically, it's a number that's too large or too small for the computer to be able to represent it. Now, what we're dealing with here is a problem that's called either an exploding gradient or a vanishing gradient, depending on whether it gets too big or too small. Now let's talk about what causes it so we can decide how to fix it. Think about when you play hot and cold. If somebody tells you you're really cold, you take large steps in the opposite direction. Well, that's kind of like what happens when you have a large error. The gradient descent optimizer tries to compensate by taking large steps, which can just exacerbate the problem. So one way to solve that problem is by making your step size really, really small. Now, this works, but it makes getting to a solution ridiculously slow. Another way you can solve the problem is by scaling the error function. This way you can take reasonable steps and still get to a solution in a reasonable number of iterations. You can experiment with step size and number of iterations, but as you can see here, we've got to a reasonable approximation of the data using this method. So that is the basics of linear regression. But what happens if it's not a line? What if it's a curve? What if your data depends on multiple features? We're going to look at that next. So far, we've been dealing with a pretty straightforward situation. We've been analyzing the number of shares based on the length of an article, and so far, it's been a straight line. But what if we had more than one feature to worry about? For example, what if the shares were related to both the article length and the title length? Fortunately, the process of using linear regression in this situation is similar to what we've already done. For example, let's take a situation in which the number of shares depends on 3 features: the title length, the article length, and the number of keywords. In this example, I've created the data so that the number of shares is something based on a function that we know. Let's see if we can create a script that predicts that relationship. So when we're dealing with a single feature, it was pretty easy to explain what the equation of the line was. It was y equals mx plus b, just as we've been saying, where m is the slope, or as we say in machine learning, the weight, and b is the y-intercept, or the bias term. Now, when we have more than one feature, finding the equation is pretty similar. In fact, we can have as many of these terms as we want. It's kind of messy, though. There's got to be a better way to do that. Well, there is. What if I told you it's still y equals wx plus b? Well, it is. It's just that w and x are now matrices. I mean, think about it for a minute. If this is w, this is x, then the dot product of w and x is, well, that's convenient, isn't it? Let's take a concrete example, though. Let's assume that the number of shares is 3 times the title length plus 2 times the article length minus 4 times the keywords. What would that look like? Well, first we have our data. So as you can see here, we have 3 rows of 100. So 3 rows and 100 columns. These are the title lengths. These are the article lengths. And these are the keywords. Each column represents one set of data, or one article. Now, if we were to look at the target, in this case the number of shares, we'd also get a matrix. This one has just one value for every article, which is the number of shares. So the question is, how do we get from this to this? Well, remember when we were multiplying matrices? It seems that what we need here is a 1 by 3 matrix so it matches this column. That way we can multiply this row by each of the 100 columns and get 100 values as a result, which is what we're expecting. And lo and behold, that's exactly what we have. So we're back to mx plus b, only now with matrices. So now that we've got this basic idea, let's look at how we can get TensorFlow to show us that relationship. So at this point, we're going to predict the number of shares for an article based on 3 features instead of just 1. It seems like this should be way more complicated than our original example, but it's really not. Most of what we're doing here is actually going to look pretty familiar. We start out by suppressing the warnings about the GPU and importing what we need. You notice that we skipped matplotlib and pyplot here because we're dealing with too many dimensions to plot anything, so we're just going to look at the numbers. Next, we'll read the data, just like we did before, but we'll use a different file because the numbers are different. All right, now before, all we had to do was reference one column of the data we read, but now we want the data to be in a matrix. To do that, we'll start by creating a matrix that's filled with zeros, but is the right shape. Now, if you're thinking in terms of XY coordinates, this is going to be a little bass-ackwards here. Instead of being 3 wide by 100 long, or 3 columns and 100 rows, which is what you'd expect, this is actually 3 rows of 100 columns each, which in this case is 3 groups of 100. I will admit, this kind of threw me when I first started, so remember, it's this many groups of that many. Now, if we run that, we can see that it's the right shape, it just doesn't have any data in it. And we can populate it by setting the value of each column to be a column of data. So now you can see that we have the data in the matrix. We can do the same thing for the shares data. First we set up the matrix of zeros, and then we populate it. Okay, so far so good. Now, whereas in the previous example we were able to just set values for the initial weights and bias, in this case we actually want matrices, so we're going to create those instead and assign them as the initial values of the TensorFlow variables. Now, we can go ahead and create the placeholders, but where before we were just setting the data type, now we also have to set the shape of the matrix. Remember, our data is a 3 by 100. And our final target is a 1 by 100. So to get the final result, we're literally going back to mx plus b, but in this case, we're using matrix multiplication. So in this case, we're using the matmul function rather than just multiply, since these are matrices, but otherwise, it is literally the same function we used before. We're also finding the error in almost exactly the same way, but this time we'll start by dividing it by 1,000, or in this case, multiplying by 1/1000th to avoid that exploding gradient. There is a slight difference here. Rather than doing a sum, we are taking the mean, which is like the average, but we are creating the optimizer in exactly the same way. We'll set the step size, then we'll create the gradient descent optimizer and feed it the step size and the error definition. Again, from there, we'll define the model and we're ready to run it. This is pretty much exactly what we did last time. We'll start by running the model to initialize all the variables. We're going to set this to run 1,000,000 iterations, but that's kind of an arbitrary number based on experimenting. Now this time when we run the optimizer, I'm going to go ahead and have it return some values so we can easily print them out. So we've got 3 variables there, and they correspond to the 3 objects that we're running. The first one is the optimizer, but we're not really using that, so we'll go ahead and use underscore as a kind of placeholder. The second one is the error, which we'll store in loss, and the third is the weight, which we'll store in w underscore value. Then we'll go ahead and print these out every 1,000 iterations. Now we can go ahead and run that. So as you can see, the loss, or the error, is gradually going down. Being able to see that is handy because you know that the algorithm is still working on getting closer. And eventually it does get us where we need to go. Now, this technique is handy because you can use it for any number of features. You can also use it for situations that aren't linear. For example, let's say the real formula was shares equals 2 times article length plus 10 times the square of the article length plus the cube of the article length. You can actually just use the same technique to figure this out, except the ingredients to the matrix would change. Instead of the different features, you'd have the different powers of the length. So when you populate the matrix, you'd do it like this. Okay, so that takes care of linear regression. The thing is, the data we've been working with so far, it's been pretty clean and pretty simple. And that's because, well, I made it up. It's what we call toy data, which means we created it to be somewhat convenient. The actual data in this data set looks more like this. But don't panic. We can work with that. In the next unit, we're going to see how. In the last unit, we looked at linear regression, which basically creates a line along which predicted values fall. We talked about the concept, and we looked at how to do it with TensorFlow. In the end, though, for our fairly simple situations, you could have done them by hand if you wanted, and if you were sufficiently masochistic. Unfortunately, the world isn't like that, so let's look at something more complicated. When we were dealing with linear regression, we talked about continuous values. For example, we talked about how many shares an article had. In this unit, we're going to classify items into discrete buckets. For example, we might have grouped the articles into 0 to 100 shares, 101 to 500 shares, 501 to 1,000 shares, and so on. To keep it simple, though, we'll just start with quote-unquote successful or not successful. Let's start with talking about features. I don't know if this was common everywhere in the world, but when I was growing up, Sesame Street had a segment called "One of These Things is Not Like the Other." It was just a quick 30 seconds where you'd see 4 objects that were similar, but not quite the same. Like 3 red children's sneakers and 1 red adult-sized boot, or 3 red balloons and 1 blue balloon. When the song was over, the different item would be revealed, but I always found it interesting because if you have trouble making decisions, like I do, you could usually make a case that if you chose different criteria, that different item would be different. Consider, for example, the 3 red balloons and 1 blue one. We could also have said 3 smooth balloons and 1 bumpy one, or 3 solid balloons and 1 with a hole in the middle. Just like the Stephen Wright joke. I went into this bar and sat down next to a pretty girl. She looked at me and said, "Hey, you have 2 different colored socks on." I said, "Yeah, I know, but to me they're the same because I go by thickness." In the next module, we'll look at the data and what features you choose, because those things matter. In today's world, not enough data isn't usually the problem. Quite the opposite. We usually have way too much data, and we have to make decisions about what we're going to use. For example, this is the full data about the online articles we're going to analyze. There are 61 different possible features or facts about each data point. Does every one of them affect the number of shares an article gets? I honestly do not know. Sometimes the correlation between 2 things is obvious. For example, the faster you drive your car, the more likely it is you're going to get a speeding ticket. You might also infer that you have a greater likelihood of getting a ticket in an area where lots of tickets are given out because it's a tight enforcement zone. I'm talking to you, Lindale, Ohio. But some features aren't quite so obvious. For example, are you more likely to get a ticket if your car is red? My dad is convinced he'll get more tickets if he puts bumper stickers on the car. Is he right? I suppose somebody can study that, but it's certainly not obvious either way. On the other hand, I'm pretty confident that there's not much correlation between getting a ticket and what color socks you're wearing, or what you had for breakfast 2 weeks ago. There's a whole science to choosing features, but basically there are 3 things you're looking for. Does the feature impact the result, either positively or negatively? Is this feature independent, or is it strongly correlated to another feature? For example, if you measured the speed of the car and the speed at which the tires are spinning, you'd throw things off because you'd be essentially counting the speed twice. Is this feature measurable and available? For example, I'm pretty sure there aren't any databases tracking the number of bumper stickers versus tickets. And if there are, I wish somebody would point me to them, because I would love to settle that one once and for all. Now, that doesn't mean that you need to have a value for every feature and every data point, just that you need to have enough of them for them to be significant. Also, keep in mind that sometimes a feature only becomes significant when it's combined with another feature. For example, you could be moving at 150 miles an hour, but unless you're driving on an actual road, it won't affect your chances of getting a speeding ticket.
Might affect your chances of smacking into something, but that's a completely different story. Most systems provide a way of creating composite features, but we're not going to get into that in our examples. Just know that it exists. Once we've decided what features to use, we have a number of different options for analyzing them to determine the classification of a piece of data. In the next section, we'll talk about a method called decision trees. One of the most obvious ways of analyzing data is with decision trees. These are the if-then statements you think of when you think about how computers work. So, for example, if we went back to our fish naming example from Unit 1, we might have an example like this. Okay, so let's analyze this fish. First, is it standard fin or butterfly? Well, these fish are standard fin koi. And these are butterfly koi. So we can see by the fins and the tail that it's a butterfly koi. Now we need to determine the color family. It's not a single color, so it's not an ogon. It does have a white body and no other colors than red or black. The orange is called red on the top, so we know it's a gosanke. There's no black, so that means it's a kohaku. Finally, you can see the mirror-like scales, so we know it's a jinrin. So we have our full title, Jinrin Kohaku Butterfly Koi. This type of analysis is also what's behind what's called expert systems, or the first artificial intelligence systems. These systems can get pretty complicated, but they can be extended as more information becomes available, making it possible to use decision trees as a machine learning algorithm. In fact, there's a whole markup language just for this kind of thing. Next, let's talk about an algorithm that's more along the lines of what you expect when you mention machine learning. It's called k-nearest neighbor. Remember Conway's Game of Life? I was fascinated by this when I was a kid. Now, if you've never seen this, this is a 0-player game, which means it just runs on its own and you don't do anything. And it creates what's called cellular automata. It works like this. Each square represents a cell that's either alive or dead. For each cycle or tick, every cell lives or dies based on how many living cells are around it. So if a live cell has fewer than 2 live neighbors, it dies of underpopulation. If it's got more than 3 live neighbors, it dies of overpopulation. If it's got 2 or 3 live neighbors, it stays alive. And if a dead cell has exactly 3 live neighbors, it gets reborn. The end result is a system that constantly changes until it reaches some kind of equilibrium. Now, k-nearest neighbors is kind of like that, in that the value it returns is going to be based on the values of its nearest neighbors. For regression, it's the average of the k-nearest neighbors. For classification, it's the most common classification of its k-nearest neighbors. So the way it works is basically by majority vote based on the value of k. For example, let's say that we want to predict whether it's raining at a particular spot where we have no weather station. What we might do is look at the weather stations around that point. This is the point that we're trying to predict, and these are the points around it where we do have weather stations, so we know whether it's raining or not in these spots. Let's say k is 3. So these are the 3 stations nearest to our target. It's raining in 2 of these spots, so we'll predict that it's raining. Thing is, if we were to look at the larger map, intuitively that does not make a lot of sense, because this seems like some pretty localized rain, and it's clear in this whole area. It's just that because k was really low, it worked out this way. So increasing k to, say, 7 will decrease the effect of this local storm, which is good. And in general, increasing k will eliminate noise, but you can't just increase it without thinking. I mean, if you had this, in this case, this storm over here is going to skew the results. So what is common in these cases is to give each data point a weight related to how far away it is from the target point. So one easy way is to give each point a weight of 1 over d, where d is the distance from our target point. In our case, it works out like this. So as you can see, even though there are more stormy points, they're farther away, so they don't have as much impact, and we get a more reasonable result.
Now, we've been looking at this from the standpoint of classification, but you can also use k-nearest neighbors for regression. For example, maybe we want to find the temperature. To do that, we'd find the average of the same points we were using before, weighted in the same way. In this unit, though, we're going to focus on classification. So let's start with that in the next module. Another method for classifying data points is called linear classification. And if that sounds familiar, it should. It's a lot like linear regression in that we're trying to find the best boundary between the two classifications. For example, say we were looking at success in terms of the number of shares an article gets. Obviously, the longer an article is out there, the more shares it's going to get. So an article that has 50 shares might be wildly successful if it's only been out for an hour, but a relative failure if it's been out there for 3 years. So let's say we define success as shares is greater than or equal to 20 shares times days since published plus 10 initial shares. This is just y is greater than 20x plus 10, or y is greater than mx plus b. So if we were to look at this on a graph, it's this area here. So this line is y equals 20x plus 10, and everything above it is greater than that. So this line is the boundary, and that's an important word, between our two classifications, successful and unsuccessful. So if we had a new data point, say 200 shares at 10 days, we could determine whether it's successful or not by plugging it into the formula. Of course, we have to have the formula first, and sometimes that's not easy. For example, what if we were looking at two different values, such as time and length? In that case, we'd have a boundary that is two-dimensional, like this. In this case, anything above the plane is considered successful, and anything below it is considered unsuccessful. But what if it's not quite so objective? What if you don't actually have the definition of successful beforehand? Well, fortunately, that's not a showstopper. We can use TensorFlow and other tools to look at existing data and create a model that defines the boundary, then determine on which side of the boundary your data falls. And that's a good thing, because now we're going to look at our real online article data, which has not one, not two features, but 61. In the last unit, we focused on predicting the number of shares an article got based on a small number of features. Now we're going to take it a step further by classifying an article as either successful or not successful based on the number of shares. And we're going to predict whether new articles will be successful or not based on the entire set of features that we have for them. To do that, we're going to use the classification version of linear regression, or linear classification, to determine the boundary between successful and not successful, and then determine on which side of the boundary our data lies. Okay, so the first thing you're going to need to do is get the data. I'm including a link for you to download the version I'm using here. So go ahead and pause while you grab that. Next, we'll go ahead and set up a script to read in the data. We'll start by creating a script, the script itself, and putting in the warning, suppression, and our imports. Next, we want to create a function to read in the data. Now, in the previous units, we were just using generic data handling using NumPy. But in this unit, we're going to go ahead and use TensorFlow's specific data handling structures. So let's create a new function, getInputs. Here we have a simple function that's going to return the features and target for each data point. We're going to extract that information with TensorFlow's loadCSV with header function. So we're going to feed that function the location of the file, and we're going to give it the data types for the target and the features. In this case, we're going to specify the target as 1 for successful and 0 for not successful. So we'll specify that as an integer, and most of our features are floating point numbers, so that's how we'll specify the feature's data type. When we do that, we create an object called dataset that's been populated with that data. Now we just have to extract the actual features and targets. When we create the dataset object,
we created an object that has certain attributes or features. For example, this car has a color attribute of red and a number of wheels attribute of 4. So in this case, we're looking for the data attribute, which has the set of features for each data point, and the target attribute, which is the label. So that's what we're getting out of it. Now let's test that out. First, we'll go ahead and read the data. Then we'll print out the features and the targets. Now let's run it. So as you can see, we've got the data here, and then we've got the targets separately. So in order to make this work, we've actually got 3 sets of data. The first set is the training data, which we'll use to teach TensorFlow the characteristics of successful and unsuccessful articles. The second is a set that we'll use to test that algorithm. And the third is our actual mystery set, for which we don't have labels. Let's go ahead and create functions to load each of them. Now, I know it's kind of weird to do it this way instead of just feeding the data file directly to the getInputs function, but we have to do it this way because of how TensorFlow is structured. All right, so now that we have the data, we can go ahead and process it. To do that, we'll first go ahead and create the classifier. That's like the optimizer we were using in Unit 2, in that it's what's going to do the actual work. The first thing that we're doing here is defining which columns are what they call real valued columns, meaning that they're continuous. So they're 2.4, 5.8, 42, and so on, rather than just buckets like red or black or successful or not successful. In this case, all of our features are real valued, so we won't specify any of them in particular. Then we can go ahead and feed that in when we create the classifier itself. Once we've got the classifier, we're going to train it. When we're training a classifier, what we're trying to do is find a boundary that fits the data, where all, or at least most, of the successful articles are on one side, and the non-successful ones are on the other side. Of course, in order to do that, it's going to need the data. And to do that, we're going to pass it an object that represents a function that returns the data we want. Since this is the training data, that will be the getTrainingInputs function. We're also going to tell the classifier that it should make 2,000 runs through the data trying to find the right separation boundary. This is kind of an arbitrary number here. We want it to be accurate, but we don't want to get into a situation called overfitting, which we'll talk about later. Okay, so now that we've fit the data and created a model within the classifier, we can test how accurate it is. To do that, we'll go ahead and feed the evaluate function the data returned by the getTestInputs function. And because we just want an immediate impression, we'll only have it run through once. Finally, what we want is the actual accuracy, so we'll go ahead and specify that and print it out. And before we move on, I promised you that we'd take a quick look at combining numbers and strings, and this is the first time that we're doing that. So here's our string, and we're including this bit in curly brackets. It's a variable, a, and then a colon, f, which means that we want to treat this value as a floating point number. There are other things we can do, like specify the number of digits after the decimal point and so on, and you'll see that later. But as you can see here, we're taking a string and we're executing a function on the string itself called format. That function takes an argument, a, which is here, and we're assigning it the value of the accuracy score. Now let's go ahead and run it and see what we get. As you can see, we've got a blah, blah, blah % accuracy, which is pretty good. So we can go ahead and see what we get when it comes to predicting success for unknown articles. Here I've got a file that has all the same data as the other 2 files, except that there's no success column. So let's go ahead and get our predictions. So we're feeding getNewInputs into the predictClasses function, and then returning that as a list. That lets us go ahead and easily print it out. Now, I don't know about you, but I'd much rather do it this way than doing it by hand. So we started out looking at analyzing data with just a couple of features that we can manipulate directly using the math. Then we moved on to letting the computer do most of the heavy lifting by fitting the data to a model and then comparing data points to that model.
Now we're going to take things a step further. Way back in Unit 1, I mentioned that there are situations in which we can just give the computer access to the data and let it figure out what's going on, finding its own patterns. Because we're not really providing the parameters of the analysis, this is called non-parametric machine learning. We're going to use non-parametric algorithms to create a simple spam filter. And of course, spam filters are kind of traditional machine learning task, but we're going to take things just a step further. Normally, we would be looking to classify emails into two categories, spam or junk mail, and ham or non-junk mail. We're going to add a third category, steak, for emails that we want to give special attention. Here's what we're going to do. We're going to take existing mails and we're going to analyze them to create the classifier. And then we're going to use that classifier to label new emails as they come in. For the spam emails, we're going to use a publicly available spam database. For the ham and steak, I'm going to use emails that I've sorted in my own inbox, with those I've archived being the ham and those I've filed into specific folders being the steak. Obviously, I'm not going to give you my emails to use in this example, but I'll show you how I worked with mine so you can use your own, which would be more accurate for you anyway because they're based on, individual contact lists and activities and so on and so forth. So my steak and ham are not going to be your steak and ham. All right, in the next module, we will get started by installing some new tools. Our next task is to classify emails, but before we get started, we're going to need some new tools. First off, TensorFlow isn't really suited to what we're doing here, so we're going to use another very popular tool called scikit-learn. And to clean the emails themselves, we're going to use a tool called Beautiful Soup. Then we'll go ahead and we'll get the data. Now, to install scikit-learn, make sure that you're in your virtual env environment, or whatever environment you're using for this, and use the pip3 installer. By including the -u switch here, we're telling pip to install any required libraries that might be missing. So we'll confirm that we really want to do this, and then that part's done. Next, we'll install Beautiful Soup. Hey, I just use them, I don't name them. And what it does, it strips any HTML tags out of the emails so that all we're analyzing is the text itself. So we'll also install that with pip3. All right, now once that's done, we're ready to start preparing our data. Now we're ready to retrieve and prepare the data that we're going to use to train our email classifier so that it can tell the difference between spam emails, which we never want to see, ham emails, which we do care about, and steak emails, which we want to prioritize. Let's start by talking about where we're getting this data. The spam is easy. We're going to download a large set of training emails from the spam database, which it provides specifically for this purpose. These are real emails that have been collected from users and sanitized for personal information. Now, for the ham and steak, you have a number of different options, and those are going to depend on your own situation. Now, I use Mozilla Thunderbird for my email, which makes it really easy to export messages as .eml files, which is how we need them for this example. If you're using some other tools such as Gmail, you've got other options, and you can get more information here. Now, I get a few hundred emails every day at my work account. Some of them are directly related to things that I'm working on, and I file them in folders. Some of them are spam, and I filter them out. Others are not spam, but they're not directly related to anything in particular, and they get archived. The good thing about this system is that I have a pre-made data set that I can use to train my classifier. All I need to do is extract these emails into a form that's easily readable by our scripts. So what I've done is created 3 folders of email. The first one is messages from several of my filed email folders. That's my steak. The second one is the messages in my archive folder. That's my ham. The third one is messages that are still in my inbox which haven't been sorted yet. Those are going to be my test messages. We'll actually analyze them with the classifier. All right, so, and of course, we have our spam. Okay, so now we've got our messages, and we're going to go ahead and process them into a form that's easy for us to process the way we've been processing our other data. What we want is a CSV file with each line representing a single email. For each email, we're going to include 3 pieces of information. They are the content of the email itself, the priority of that email, and a unique ID that helps tie them together. So let's look at how we're going to do that. We'll start by importing the new libraries we used in the last module. We'll start with Beautiful Soup, which in this case which we'll use to strip out any HTML and leave us plain text. Then we'll import a couple of pieces of scikit-learn. The first is going to help us really easily split up our training data into a training set and a test set so we can validate our accuracy before we move on to the actual analysis. Next, we'll go ahead and import the count vectorizer, which is going to help us analyze the text itself. Finally, we'll go ahead and import some more familiar pieces. The first is OS, which lets us do some operating system commands, such as reading all files in a directory. Then we have RE for regular expressions, which we'll use to help pull out the actual text from the emails. Next, we'll get sklearn and pandas. Next, I'm going to set up variables for the directories where I've got emails stored. Okay, now the idea here is that we're going to create a single array that includes all of the emails, so we can easily write that array to a file using pandas. Each of the elements in the array is going to be an object that includes the ID, email, and priority. The priorities are going to be pretty simple. Spam is a -1, ham is a 0, and steak, our priority email, is a 1. All right, so we'll start by creating the empty array and initializing the ID value, which will increment for each email. So what we're going to do here is load each group of emails with its own priority level, incrementing the ID as we go. Let's go ahead and start with the spam. We'll start by looping through the spam directory and outputting the file name. Let's make sure that worked. Great. Now we want to go ahead and read the emails, so we'll open them and get all the text from the file. All right, let's make sure that part's working. All right, that's pretty ugly. So let's see what we can do to clean it up a little bit. Let's go ahead and create a new function called email to words. We'll put it up above our processing so it's out of the way, but it's still available. Okay, so the first thing we want to do is we want to pull out the actual text and get rid of any HTML tags, which we'll do with the getText function from Beautiful Soup. We're specifying LXML here because the HTML is a special case of XML. Okay, so now let's get rid of any punctuation and so on and replace it with spaces. We're using a regular expression here, so let's take a quick moment to explain what's going on. First off, we're substituting any character in email text that matches this expression with a space. We can decode the expression itself this way. First, the brackets mean any one of these characters, which in this case is all letters from lowercase a to z and uppercase a to z, but then this caret here means do the opposite. So any character that's not a letter is going to be replaced with a space. Next, to make things a little more regular, we're going to change everything to lowercase. Now, at this point, we've got a bunch of words and spaces and probably lots of places where we have multiple spaces. So what we're going to do now is make the string into an array by splitting it on the spaces and then join it back together into a string by adding just a single space between words. That'll take care of all of our multiple spaces and compress them into one. Okay, one last thing we need to do here. Some emails are going to come in using different encodings, which will show up as funky characters. So we're going to go ahead and encode the whole thing as ASCII to get rid of that. And then finally, we'll return this new text string. So now let's print out this cleaned up version. And we'll run it. All right, that looks way better. All right, so now that we know we can get the data, we need to go ahead and create an object so we can add attributes to it. So we'll set the ID attribute and then increment it by 1. Now we'll set the actual email attribute to the words of the email. And this email is spam, so we'll set the priority to -1. Now we want to add this email object to the array of emails. And finally, close the file. Now, just to make sure we know what we have,
output the number of emails and a sample. Now we're going to write all this data to a file. So first we'll turn it into a data frame, which is the pandas structure. And then we'll write the data frame to disk. We'll specify the file we want to save it to, and then we'll turn off indexing, which would include names for each email, and we'll specify ASCII for the encoding. Because we're using Python 3, and the default would otherwise be UTF-8. Okay, let's run this and see what happens. Great. Now if we open the emails.csv file, we can see the results. That looks nice. Okay, so that's the spam emails, but we can do the ham and the steak really easily. We'll start with the ham. You notice this is the same as for the spam, except we're looking at the ham directory, and also now the priority is 0 rather than -1. We can do exactly the same thing for the steak. All right, now if we run it, we can see we have way more emails. The last thing we have to do is put all this together and process our test emails. So now we've created a new array, and that's what we're using to hold and save these emails, rather than the all emails array, which holds the training data. So we can run this. So now we have our training data and our data to analyze, and we're ready to go ahead and build the classifier. That's what we're going to do in the next module. So now that we've prepared our emails for analysis, we can go ahead and classify them. To do that, we're going to touch on two new topics: representing non-numeric data and working with multiple algorithms to determine an answer. We're going to do a deep dive into each of those topics later in the course, but for now, let's get a basic idea. The first thing we need to understand is how we're going to tell how similar our target text is to our training text. To do that, we're going to vectorize it. For example, we might take to be or not to be, and this would become, so the vector would be 2211. If we also had to improve is to change, to be perfect is to change often, we'd have or 412211. So if these two were part of the same group of texts, it would be more like this. Or 2110000 and 4100122211. Now, even though these aren't in three-dimensional space, they still point to a particular place. So if we wanted to, we could find the so-called distance between them, which represents how similar or different they are. We can use this method to compare our training set of emails with our target set of emails. Now, this is called creating a bag of words, and obviously this is pretty rudimentary. I mean, it relies only on the number of words rather than the actual meanings. Synonyms will be treated as completely different words, so that meaning is lost. Besides that, the position of the words in relation to each other are irrelevant in this case. So you can see that there may be some misunderstanding there, and there are definitely situations where punctuation makes a difference. Later, we'll talk about other methods that take all this into account, but for now, we'll go with this more simple version.
So far, we've been concentrating on supervised learning, which involves the algorithm taking what we already know and applying it to data where we don't have the answer. Now we're going to take things one step further. Not all machine learning can be done using existing examples. Sometimes we need to let the algorithm figure things out on its own, seeing patterns we didn't even know were there. For example, we can let the program find clusters of items that are similar. If I were to ask you what clustering is, you probably have an intuitive sense. It's about grouping similar things together. In a lot of ways, this is similar to when we were looking at classification, in that it's a lot like the which of these things is not like the other problem. The difference, though, is that with classification, we know what we're looking for, and we're asking the algorithm to analyze the data with that in mind. For example, we looked at classifying emails as spam or not spam, and in doing that, we were able to give the algorithm examples of both. With clustering, however, we're not making any assumptions at all, and we're letting the computer do all the work in figuring out what groupings there are. So in the email example, instead of feeding in the emails and whether or not they were spam, we would have just fed in the emails and let the algorithm decide what the groupings were. It's possible that it would have come up with spam or not spam, but it's just as likely that it might have grouped the emails by sender, or by subject line, or by where they came from. Or it might have grouped them by something we hadn't even thought of, like the topics of conversation, or even some combination of all that. And in fact, in many cases when we're clustering, it's for situations in which we have data that has a lot of different features, and it's not easy to simply look at a graph and circle points that are close together. For instance, going back to our first example of successful content, we might ask for clusters of articles, then look at what those clusters were based around. Maybe we'd find out that on Tuesdays, long articles with short titles and lots of keywords did well, but on Wednesdays you could still use lots of keywords, but only on short articles with long titles. This is not something that would be easy to figure out on our own, but the algorithm can do that. In this unit, we're going to look at a couple of examples that are admittedly a bit simpler than that, but you'll get a feel for how this works. First, we'll cluster some artificially generated graphical data, and then we'll look at using open source text analysis tools to detect trending topics on Twitter. Perhaps the most common clustering algorithm is called k-means, and we're going to talk more about that in Module 4.3. But let's start by looking at clustering in general. There are two basic ways of clustering data points. I like to think of them as bottom-up and top-down. Bottom-up clustering is where you take each point and you combine it with the point closest to it to make a cluster, and then you take those clusters and combine them, and so on and so on. It's kind of like when you have rain on a window and the drops gradually come together. In this case, you keep combining until you eventually reach either the minimum number of clusters you want, or you decide that the distance between points in a cluster is so big that the points really aren't related. Top-down clustering is called the divisive approach, in that you start out with one big cluster and you gradually split it up. This is what we're going to do in this unit. Basically, you choose a location for the cluster, then assign points to that cluster based on their proximity to it. In this case, you'll need to decide how many clusters you want first, of course, so it requires you to have a little bit of knowledge about the system. Though you can always run it, analyze the results, then change your mind and run it again, which is how it works in a lot of cases. In the first part of this unit, we're going to focus on the most common of these algorithms, k-means. When I first started working with machine learning, I got to k-means and I got really confused because, like you, I'd just gotten through k-nearest neighbors and I thought, wait a minute, is this the same thing? The answer is no, of course, and it's a little unfortunate that they've been named so similarly because the k in each of them means totally different things. K-nearest neighbors, as we discussed in Unit 3, is a supervised learning method used for regression or classification, where k refers to the number of points that we take into consideration to determine the value or classification of a particular point. K-means, on the other hand, is an unsupervised learning method used for clustering, where k refers to the number of clusters we ultimately want to see. Now, one of the best explanations I've ever seen of this, and I've seen it in a bunch of places, so I don't know who came up with it, regards deciding where to put businesses or organizations that rely on proximity to their customers in the physical world, like pizza joints or hospitals or police stations or schools. Let's think of the children and say we're going to build some schools. So let's say that we have 150 houses and we're going to build 3 one-room schoolhouses. Mostly because if I put real numbers in this, we'd just have great big blobs rather than something that actually makes any sense. So if we were to map out the houses, we might have something like this. So there are any number of ways we might break up these territories. We could just do it in 3 big rectangles. Or we could just choose some random shapes. But those aren't necessarily going to be best for the kids who are walking to school. Take this kid, who has to walk all the way over here, even though the nearest school is practically across the street from his house. So the k-means algorithm works like this. First, you choose arbitrary locations for the center of each cluster. These are called the centroids. So let's say we propose schools in these 3 locations. Now let's assign each house to the nearest school. So now each student is walking to the nearest school, but the schools themselves aren't exactly centrally located in their districts, so some students are walking much farther than they should have to. So now let's move the schools to the average position of all the houses so that it's centrally located in the district. Thing is, once we do that, something interesting happens because now it looks like some of the houses are closer to a different school than the one that they're assigned to. So let's do this process again and assign houses to the nearest school. And of course, we need to go ahead and recenter the centroids. So basically, we keep doing this until the centroids stop moving. So that's how we wind up with the most efficient clusters, or in this case, school districts. Now, in this case, we're clustering objects that are laid out in 2 dimensions. We can do this with any number of dimensions, it just gets tough for us to do it manually. Fortunately, we can let the computer do this for us. We'll look at doing that next. In the next few modules, we're going to look at getting TensorFlow to perform k-means clustering for us. Now, there's no one right way to do this. I'm going to show you a pretty straightforward way that lets you see how k-means works, and makes use of some functions we haven't used before. Once you're really comfortable, you may want to look at using some of TensorFlow's other features to streamline this process, but I promised you way back at the beginning of the course that I was going to keep it simple, and I meant it. So, what we're doing is we're going to create some sample data and then animate a graph to show the k-means process. Now, before we start with the actual analysis, though, let's take a quick look at how Matplotlib does animations. Once we've done that, we can go ahead and add the actual data to the animation. Assigning points to a centroid in k-means. At this point in our quest for k-means clustering, we've created a script that includes a function to be executed multiple times. It happens to be the Matplotlib animation function, but that's just a matter of convenience. We're going to use it for our clustering operation. The next thing we're going to have to think about is how to associate each of the data points with the proper centroid. The easiest way to do that would be if we added a column, so to speak, to note what centroid each point belongs to. Now remember, we have 3 clusters, so our centroids object has dimensions of 3, 2, or 3 groups of 2. What we want is to be able to have each point be able to reference one of those centroids in particular. So instead of having a giant pile of points, we want to group them together with each new pile corresponding to a centroid. Now, in order to do that, we're going to need to figure out which centroid is closest to the point, and we do that by taking the displacement between the 2 vectors. Now, remember, we're dealing with vectors which have a magnitude or length and a direction. So displacement is just the distance between the 2 points, or the length of the vector between A and B. Now, mathematically, we can figure that out by subtracting one vector from the other. We want to do that with each of our points and our centroids, so that we wind up with a tensor that shows all of the displacements. Unfortunately, we have a problem. These 2 vectors aren't shaped in a way that's going to give us what we want if we subtract them. Instead, we need something like this. To get that, we're going to use a TensorFlow function called expand_dims. We'll look at that in the next module, so if you're already familiar with it, feel free to skip ahead to module 4.8.
In Units 1 through 4, we covered basic supervised learning, where we provide the algorithm with labeled data and train it to correctly identify unlabeled data, and unsupervised learning, where we provide the algorithm with unlabeled data and ask it to find any patterns in that data. Now we're going to tackle one of the most common forms of machine learning today, or at the very least, the one that's getting the most attention. That's neural networks and deep learning, which involves a number of interconnected nodes that work together to find complex patterns that are inherent in large amounts of data. Starting in Unit 6, we're going to go ahead and build neural networks to perform tasks such as handwriting analysis. But before we start programming, we want to have a good mental model of just what neural networks are and how they work.
To do that, we're going to play a little. It would be nice if all relationships between different values were easy to establish, because then it would be simple to extrapolate values for missing data points. For example, if a hotel room is $100 a night, you can easily figure out your bill by multiplying the number of nights by $100, so the cost is 100 times the number of nights. The amount of noise you hear is equal to the noise level of a distance source divided by the square of the distance plus any noise at your location. You could easily use these equations to define too expensive versus affordable, or too loud versus tolerably loud. You could even work backwards from a graph like this to determine the relationship so that you can label new data points. That's what we did with supervised learning. In the real world, however, things aren't usually that simple. So what do you do if you have a more complicated relationship, like this one? In reality, in order to make a shape like this, you're typically going to have to combine multiple formulas, usually varying their strength. For example, let's say we have a pattern of all values of x that are less than 0 are orange, and all values of x that are greater than 0 are blue. Then let's say we have a pattern of all y that are less than 0 are orange, and all y that are greater than 0 are blue. If we were to combine these two patterns and give them equal weights, we have a diagonal with the lower left as orange and the upper right as blue. Now, this is actually a very, very simple neural network with two nodes. If we were to vary the weights of these two nodes, we'd see differences in the output. For example, if the horizontal weight was only half of the vertical weight, we'd get a more vertical diagonal line. And of course, if the horizontal weight was 0, we would just see the vertical line because the horizontal line had no effect on the final output. So, in a nutshell, that's how neural networks work. But in general, they're a lot more complicated. So, to see how all of the different pieces can interact to give us some pretty complicated patterns, we're going to play with Google's TensorFlow Playground, which lets us visually create neural networks. We'll see that in the next module. In the last module, we introduced the idea that a neural network was basically a combination of different patterns to make a final output pattern. In this module, we're going to use the TensorFlow Playground to dive a little deeper into how neural networks work, where deep learning fits into the equation, and so on. So start out by pointing your browser to http://playground.tensorflow.org. Now, when you first start up the Playground, they give you a sample to work with. Let's take a look at the interface, starting with the main body. This large image on the right is the training data we're trying to emulate with the model. Over here on the left, you can see that there are 4 sample classification datasets you can play with. There's nothing particularly special about them, except that they're complicated enough that you would need a neural network to figure them out. Here you can specify how much of the training data to split off into a test dataset. You can also specify an amount of noise and the batch size, which we'll talk about later. You can also regenerate a new set of data that uses the same shape, as you can tell if you click the Regenerate button. Here in the center, we have the actual nodes or neurons that are in use. This first column shows a number of different models you can use as your base models. We've got x1 and x2, which are divided horizontally and vertically. Now, models x1 and x2 may look familiar because we use them in Module 5.1. We also have additional models. For example, this is x1 squared, which makes sense if you think of blue as positive and the orange as negative, so x1 squared is going to be all positive. Then we have x1 squared, x2 squared, x1 times x2, and also a couple more complicated functions like sine x1 and sine x2. We'll talk about how you choose in a little while, but let's keep exploring the interface. This second and third column are what's known as hidden layers, and we'll talk about them in Module 5.3. For now, though, let's go ahead and remove these hidden layers by clicking this minus sign here. Okay, so let's start with this data set here because it's pretty simple and we just want to see how the process works. So click X1 and X2 to turn them off. All right, so our goal is to try and replicate this pattern using one or more models. So let's start with x1 times x2, which is similar to what we're looking for. Now, If you look up here, you can press the play button to actually run the model. And by that, I mean that the network continually checks the accuracy of the model against the test data and makes adjustments to the weights as appropriate to try and get as accurate as possible. Each of these adjust check cycles is an iteration or an epoch. As you can see, the results start to look good pretty quickly. The orange area, which is where the model predicts the values will be negative, is matching up to the orange points, and the blue area, where the model predicts the values will be positive, is matching up to the blue points. If we look along the top here, we can see a few things. First, when we hit play, we can see that the number of epochs is going up pretty quickly. This button lets you step through it one epoch at a time. Here we see the learning rate, which is the same thing as the step size we used in Unit 4. Now, these, activation and regularization, I'm going to ask you not to worry about for now. We're going to talk about them in Unit 9. Finally, you can choose between classification, which is what we're looking at, and probably the way neural networks are most often used, and regression. So, neural networks will work for regression too, not just for classification. Finally, coming back down here, we can see that the results have converged pretty quickly, and that the training and test errors are pretty low. As for these boxes down here, show test data does exactly that, and discretize output gives you a more definite orange or blue rather than percentages for each spot, with higher likelihood percentages resulting in darker colors. So, what has actually happened here? Well, you remember how in Unit 3 we used y equals wx plus b to determine the formula for the separation between two different classifications, and then TensorFlow iteratively determined the values of w and b? Well, that's essentially what has happened here. TensorFlow has gone ahead and figured out the right w, or weight, and the right b, or bias, to make our model fit the data. Of course, in this case, that wasn't very complicated because the data and the model were the same shape. Most of the time, though, a data set can't be represented by a single model, and in the next module, we'll look at how to use multiple nodes to combine models. In the previous module, we looked at the TensorFlow playground and used it to fit a very simple model to a very simple data set that matched it pretty closely. In this module, we'll look at dealing with more realistic, that is, more complicated situations. So we started out using the data set with 2 orange and 2 blue squares. If you were to reset the data and change to the first data set with the blue circle surrounded by orange and then press the play button, you'll see that no matter how many iterations we run, no matter what weight we choose, this model is never going to approximate this data set. That's because each node is a very specific shape. In this case, the shape is a checkerboard, and making it stronger or weaker isn't going to change it into 2 concentric circles. To do that, we're going to have to combine it with a second shape. In other words, we need to combine a couple of different models. Just to make it interesting, let's try the first 4. It's a completely arbitrary choice. Let's just see what happens. Now, when you do this, you're probably going to get a different image than the one you see here. This is because when the nodes get added, they're assigned a random weight, which seems a little weird until you remember that we did exactly the same thing when we were doing our gradient descent problems. We were just arbitrarily choosing a value for w to start off with, and then letting the optimizer fix it. Now, you can see the weight for each model if you hover over the line from the node to the output. Remember, that weight determines how heavily this individual node affects the output. If you click this reset button here, the playground will shuffle the weights for you, so you can see how changing the weights affects the output. So this issue of the weights is really important because, again, those weights are what determines what the final output is going to look like. For example, we can click the top line to edit that weight and press the up arrow on the keyboard to see how increasing the weight for this node makes the output look more and more like the original model. Okay, so we can mess around with the weights ourselves trying to find the right answer, but that would be kind of silly. So instead, let's just let TensorFlow do it for us. So we can just press start. And we really cranked up that first weight, so this is going to take a long time. And I'm not the most patient person. So one thing we can do is crank up the learning rate to speed things up. Let's bump it up to 0.1. Yeah, that's still taking too long. Let's take it to 1. Okay, that's better and really fast, but I don't like the fact that we had to do so much manual intervention. I want to go ahead and check that we really do have the right model. So I'll reset it, and this time I won't mess with the weights or the learning rate. So if we run it again, we can see that TensorFlow does manage to come up with the answer on its own. And if we look at this result, we can see that the top 2 models, X1 and X2, have very, very small weights. That means we don't actually need them to get the right answer. And if we remove them, we still get a pretty good model. Okay, so what does that say to us? It says that most of the time, not always, but most of the time, there are multiple ways that you can get where you're going. So if you have a sufficiently flexible model, you can tweak it to get almost anything if you train it right. Now, in the next module, we'll look at increasing flexibility and therefore trainability by using hidden layers. In the previous module, we looked at how we can combine multiple nodes, each with their individual model or shape, to output a new shape. In this module, we're going to look at using this technique to get more complicated outputs by adding additional layers. These layers are called hidden layers, and they're used to give us additional flexibility and complexity for our outputs. In the previous module, we were using the first 4 input nodes, and we were able to use them to emulate dataset number 1, the concentric circles, pretty well. This time, though, let's see what happens if we go with a totally different shape. Specifically, let's look at dataset number 2, because it's different enough that it should really let us know whether we have a complete solution. Now, if you run it, you'll see that we're not quite getting what we want. There are still a lot of blue points in the dataset that are in the orange area, which means that the model thinks they should be orange. So this model is definitely not accurate. Interestingly, you might not wind up with something that looks like this. You might get blue on the other side, for example. The important thing is that this model, or arrangement of nodes, is simply not flexible enough for our needs. So instead, we're going to start adding hidden layers to increase that flexibility. So what we can do is come over here and click the plus sign by hidden layers to add a new hidden layer. Now, why is it called a hidden layer? It's called a hidden layer because you're not actually controlling the input to it directly. Instead, the nodes in a hidden layer are a combination of the nodes that feed into them. As we go along, we'll see why this is useful. So let's look at this. Before we added the hidden layer, we had 4 nodes which combined, based on their weights, to form one output. Now, each of these nodes in the hidden layer represents the output of the nodes that are coming into it, adjusted by those same weights. You can see what each of these nodes represents by hovering over it, like this. And then those intermediate steps in the hidden layer combine to form the final output based on their own weights. So if we go ahead and run this model, we can see that TensorFlow figures out weights that will use the nodes to produce the pattern that we want. That is, the pattern that represents the training data. Now, most of these patterns are pretty easy to get with these nodes. For example, we can switch over to the first one and run it, and we can see that TensorFlow adjusts the weights to give us the new shape based on the training data. We can do the same thing with the third one. But the fourth one, the concentric spirals, that's a toughie. We can try and train this network, but really, it's not getting very far, as you can see. The model isn't producing a pattern that's anywhere close to the training data. We can also add additional layers if we want to. So let's try adding 3 additional layers. We can add more nodes. Let's add 2 more nodes to the 4th layer. Now, you may have noticed we've got this big, small pattern going on here. There are a ton of different things you can do with these neural networks and how they're arranged. For example, sometimes you want to gather everything together into a single node and then split it off again. There are a lot of different reasons behind the shape of a neural network, and we'll talk about some of them as we go along. But for now, just know that there is actually some rhyme and reason to how the various nodes and neurons are structured. But the network is still producing a pattern that's not as accurate as we want it to be, and we can tell that because this point is totally wrong, and so is this one. In order for us to consider the overall model to be accurate, it should be accurately predicting whether a particular point should be blue or orange. Let's see what happens if we give TensorFlow some more horsepower to work with. We'll go up to the maximum 6 hidden layers and we'll make them a little bigger. Now, that's pretty impressive. TensorFlow found the pattern, that is, the accuracy against the training data got really good in just a couple hundred iterations. The thing is, while it does match our training data, our human brains can see it's not quite correct. For example, it seems pretty weird that these two tails just stop. If this were a real pattern, we'd expect them to keep going, but according to the model, they don't. This is a condition that's called overfitting. We're going to talk more about overfitting in Unit 6, but let's see if we can get this model a little bit closer. First, let's go ahead and expand all of the hidden layers as much as we can so that TensorFlow has the maximum amount of flexibility. And we can try running this by itself, and we can see it's getting a little better. The spirals are getting a little bit more regular, but it's still not right. Now, we can't add any more nodes, so we'll have to try something different. In the next module, we'll look at the activation function, what it does, and what some of our options are. So far, we've used TensorFlow Playground to create a neural network. We've looked at how nodes are combined using weights to create an output, and we've looked at how those outputs can be created using hidden layers to create more complex models. Even so, we're not quite ready to declare victory. There's one more piece of the puzzle we need to understand, and that's the activation function, which defines how the output of each node gets passed along within a neural network. And we've talked about the weights of what's coming out of these nodes, but what is it that's actually getting weighted? You might think that it's literally the sum of these values coming in, but usually it's not. The very first neural networks used what's called the perceptron. And the perceptron was a really simple activation function that turns a neuron completely on or completely off, like a digital value. So when you're using the perceptron, the output of a neuron would be either 0 or 1, and it's decided like this. You've got these values coming in, and they make a vector. You've also got a weight matrix and a bias, just like before, so you can use the whole y equals wx plus b. And the perceptron says that if wx plus b is greater than 0, output 1. Otherwise, output 0. So if wx plus b is greater than 0, the perceptron, and thus the node, returns 1. Otherwise, it returns 0, and the neuron doesn't fire. So you get a graph something like this. The perceptron, however, is just one version of an activation function. So far in this unit, we've been using the tanh function, or the hyperbolic tangent, which is a little more complicated. Hyperbolic tangent gives us a function something more like this. So as you can see, at 0, we get 0 output from the neuron. As the value gets more positive, we see a bigger and bigger value until we get to 1, where it levels out, and then gets multiplied by the weight, of course. And then the same thing happens in the other direction for negative values. So you can go ahead and try the different activation functions here at the top of the TensorFlow Playground. But we're going to set TensorFlow to use the rectified linear units activation function, or ReLU. ReLU means that if a value is negative, it returns 0, and if it's 0 or greater, it returns the actual value. So the output function looks like this. So let's go ahead and set the activation function to ReLU and run it again. Now this is going to take a while, but we see that it does give us a better representation of the pattern. As you can see, the blues are now continuing on around the top, and the orange is starting to get a tail that extends past the actual sample data. So we're looking pretty good. It actually takes a while for this to get to the point where it looks really great, but it eventually does. So those are the basics of working with neural networks. Feel free to play around here and see how things work. In the next unit, we're going to go ahead and put together an actual neural network to do handwriting analysis. We'll start with that because it gives you a good idea of how neural networks work on real problems. In Unit 5, we use the TensorFlow Playground to get an intuitive feel for how neural networks work. Now we're going to use TensorFlow itself to build an actual neural network to do something much more concrete. Neural networks and deep learning are good for recognizing specific patterns, such as identifying images or other classification tasks. In this unit, we're going to look at the techniques for doing that by putting together a handwriting recognition example. We'll use the well-known MNIST database. According to Wikipedia, the MNIST database, or the Modified National Institute of Standards and Technology database, is a large database of handwritten digits that's commonly used for training various image processing systems to build a program that looks at graphics of handwritten digits from 0 through 9 and identifies them. In doing that, we'll look at how to encode non-numeric data, including one-hot encoding, how image recognition relates to a neural network, creating a deep neural network in TensorFlow, how to define the loss or error, and actually performing the handwriting recognition. We'll also talk about what overfitting is and how to prevent it. When you've finished this unit, you'll have a good idea of how neural networks work and how all of this applies to other real-world problems. In the next module, we'll get started by looking at non-numeric data and how we can encode it or represent it in a way that lets a computer work with it. Although we've mostly dealt with numeric data in this course, such as the length of an article versus the number of shares it got, we've also briefly dealt with the notion of non-numeric data in the form of matrices that represent sentences or paragraphs. This transformation of words into mathematical objects, that is, matrices, was one example of encoding non-numeric data. In this example, we're going to take this a step further by looking at how to encode images in such a way that we can work with them mathematically. To see this in action, we're going to build a handwriting recognition system. Now, this is definitely not new and novel. If you look into how to build neural networks, especially with TensorFlow, chances are you're going to find an example that does handwriting recognition, and there are a few good reasons for this. First, image recognition is a real practical use case that comes up pretty often. And second, it's a task you can actually tackle yourself pretty easily with existing tools. In this case, by limiting our identification to just 10 cases, that is 0 through 9, we're simplifying training considerably. But the concept is exactly the same, not just for numbers or Roman letters, but also for characters from other languages. A second reason is that there's a great data set for this built right into TensorFlow. It's called the MNIST database, and it consists of 70,000 images of handwritten numbers from 0 to 9, broken up into training, testing, and verification data sets. So you won't be on the web posting in forums saying, "Does anybody know where I can get a good data set for this?" A third reason we're going to look at handwriting recognition is that it's a really good example of a topic that comes up very often in machine learning, which is working with non-numeric data. I mean, seriously, most of the examples that we've looked at so far have involved numeric data. Even when we were doing classification, we were essentially classifying based on numbers, and the classifications themselves could be looked at as discrete numbers. But how do you do math on this? That's what we're going to look at in this unit. So, according to Wikipedia, the MNIST database, or the Modified National Institute of Standards and Technology database, is a large database of handwritten digits that's commonly used for training various image processing systems. So, basically, we're talking about 70,000 28 by 28 images of handwritten digits, like these. Now, there are any number of ways to represent this information. For example, if I were to take this 7 and save it as a JPEG, and then open that JPEG in a text editor, it looks like this. If I save it as a PNG and I do the same thing, it looks like this. It's still gibberish, but you'll notice it's different gibberish. The fact is that when I open these files and I get a 7, it's only because the computer understands how to read these two formats. In fact, if you download the data set and open it, you get a completely different set of gibberish that you have to interpret in order to see the data as images in the first place. So the actual representation isn't important as long as you're consistent in reading and writing it. Now, for us humans, one really convenient way to represent this is as pixels. Now, our brain interprets that as a 7 because we know that 7s have a horizontal line here and a vertical or diagonal line approximately here. Now, if there was a curve over here, we'd be more likely to think of this as a 9. In fact, let's save this 9 for later. Okay, so Going back to our 7, this is a format that our brains understand, but it's not very convenient for math. Or is it? What if instead of these raw pixels, we replace the black with 1s and the white with 0s? Still looks like a 7, right? Well, sure it does. But it also looks like a matrix, and a matrix we can do math with. Of course, this is pretty simple. I mean, in this case, you'll notice that we're dealing with just 0s and 1s, which is great if you only have black and white pixels. But what if you have various shades of gray? Well, in this case, we can still convert this to a matrix, but we won't have just 0s and 1s. Maybe we'd have values from 0 to 255. Or a normalized version that has everything down to a fraction of 1. Regardless, we can still do math with this matrix just as we've been doing all along. All right, so let's get even more complicated. What if it's now in color? So let's see, we made a color change and we even added some detail to the background to make it a little more interesting. I suppose you could turn this into a matrix like the last one by choosing numbers all along the UV scale, but when it comes to computers, the usual way to do this is by separating the image into 3 channels: red, green, and blue. And each of these layers has its own matrix. In fact, we can put these 3 matrices together into one big matrix, which we can act on mathematically, even though it is kind of nasty to look at. Fortunately, TensorFlow has some built-in functions for that, which we'll look at a couple of modules from now. But the important thing is to understand that no matter how complicated and non-mathematical something looks, we can always turn it into something we can look at mathematically. Now, remember how I was telling you back in Unit 1 that one of the things that bothered me about physics is that the math doesn't always seem to make sense with the real world, but you still have to trust it? Well, that's something you have to think about here as well. Let's go back to our simple 14 by 14 matrix of 1s and 0s. So, when we look at this 14 by 14 matrix, it makes sense that this represents a 7. Thing is, it's only because we decided we're going to do a 14 by 14. If we were to reshape this matrix to, say, 28 by 7, we don't change the data. We could change the shape again, and it still wouldn't change the data. The reality here is that all we have is a string of 0s and 1s, and it doesn't matter how we arrange them as long as they're in order. In fact, we could even make this one flat line of 196 0s and 1s. It's still a 7. It's a little harder for us humans to see that. Okay, it's pretty much impossible for us to see that, but it's true. All the information is still there. For example, remember that 9 we were playing with earlier? Well, we can turn that into a matrix and then flatten that out. And we can see that it's very similar to the 7, but just a little bit different. Okay, so why would we do this? Well, for one thing, it's a lot easier to do math on a one-dimensional matrix than a two-dimensional matrix. For another thing, once we've got these digits as one-dimensional matrices, we can store them all together in a single matrix. So those 28 by 28 images in the MNIST database, we can store them as, 70,000 groups of 768. Once we have that 2D matrix, we can easily perform a lot of math on it. Okay, so what did we learn here? We learned a couple of important lessons. Number 1, anything can be made into a matrix so we can do math on it. Number 2, the shape of the matrix doesn't matter as long as we're consistent. Now, those lessons are going to be very important when we start working with this data in a neural network. But before we talk about that, we should talk about one more way to encode non-numeric data for use in these operations: one-hot encoding. We'll talk about that in the next module. In the last module, we talked about how to encode graphics so that we can use them in mathematical operations. But what about the values that represent what those digits actually are? After all, there's no point in training the network to recognize a 7 if you can't tell that it is, in fact, a 7. One way to solve that problem is through the use of a method called one-hot encoding, which is a means for indicating what bucket an item belongs in. In this module, we'll look at how one-hot encoding works and how it relates to neural networks so that when we use it later on in our handwriting analysis, it'll make sense. As it happens, we've already been using something similar to one-hot encoding. Remember when we were looking at our sentences and loading different words by putting a 1 in their column? That's similar, but not quite one-hot encoding. Yes, it does have 1s in the relevant columns, but one-hot encoding is special because you only have a single 1 in the column for the appropriate value. So, for example, if I were to have a series of digits, I could encode their values like this. Now, this gets important when we're doing a classification task like handwriting recognition because we can use these values to help determine what our final value is. For example, let's say we do a bunch of operations and we wind up with a series of values that represent the probability that a particular image represents a particular object. If we represent the highest vote as a 1 and the rest as zeros, we can figure out what value it represents by multiplying by all of the possible values. If it's not the right value, it'll evaluate to 0. If it is the right value, it'll evaluate to 1. So in our case, we have a data set that includes the matrices for our images that matches up with the data set of one-hot labels to tell us what they actually are. In the next module, we'll look at how all of this works in the context of a neural network. So far in this unit, we've been talking about how to represent images in a way in which they can be manipulated mathematically. Now let's talk about how all this relates to a neural network. Now you may remember that when we were working with the TensorFlow playground in Unit 5, we were essentially creating matrices of weights that created a certain pattern. The outputs were more complicated than what we're doing here, but the concept is the same. We created an array of neurons, and each of them was essentially a vote for a particular value going forward. The size of the weight coming out of that neuron determined the strength of that vote and how much of that pattern was passed forward to the next layer. It works the same way for computer vision problems like the one we're working on now, or even more complicated ones. For example, right now we're just trying to identify images that are one of 10 different classes. What if we had generic images and there were thousands or even millions of possibilities? Those patterns that are getting passed forward might be, I see a face, or I see a car, or I see a fish. And those votes might be built up from votes of smaller features like I see an ear, or I see a wheel, or I see a fin. In the handwriting recognition example we're working with in this unit, we're doing the same thing, but on a much smaller scale. Instead of a face or a wheel or a fin, maybe we're looking for a straight line along the top, or a group of pixels around the outside, or 2 verticals and a horizontal. And all of these votes can be both positive and negative. For example, if an early layer sees a wheel, the final answer is probably not going to be fish. And if it is, that's one weird fish. Similarly, if our graphic has a lot of pixels in the center of the image, it's probably not a 0. So we can create filters that we can apply to an image to help determine what it is. So for example, we might have filters like this. If we apply each of these filters to an image matrix, we can figure out what the digit is. Of course, this is incredibly simplified. It's ridiculously low resolution, so unless the image is pretty exact, we're probably not going to find it correctly. In the real world, where we have to take into account variations, the filters look much more like this. Now, if we have those filters, determining the answer is easy. We just multiply. Getting the filters, that's the tough part. And that's why we have a neural network. Now, just like when we were finding weights before, we initialize the neural network with random values, then use a method like gradient descent to decrease the loss until it's minimized and we get the best, smartest filters we can make. Now, there are several techniques we can use to do this, including fully connected layers, hidden layers, convolutional layers, and pooling. We're going to look at all of those as we build this handwriting recognition problem out in TensorFlow, starting in the next module. In the last unit, we took our first look at dealing with data that wasn't quite numeric by looking at how to treat images as mathematical matrices. Of course, in the real world, machine learning routines have to deal with a whole range of information types. So in this unit, we're going to look at some of the different types of data you may come up against and how you can deal with them. For example, you may be trying to identify the subject of an image, or do speech recognition, or even predict trends in data over a period of time rather than simply analyzing one static set of information. This process involves looking at both encoding, which is converting data into a form that makes it possible to work with it, and representation, which is the relationship between information and the actual data you see, such as a 0 or 1 that represents a single bit in a computer. In this unit, we'll look at different types of data and how they're both encoded and represented. We'll also give you a general idea of how to work with various kinds of data in the context of machine learning. Now, because they're the most common, let's start with numbers. In the next module, we'll look at some of the different types of numeric data you might encounter. On the one hand, it may seem like numbers are the easiest type of data to deal with when it comes to machine learning. After all, we're doing math, so why wouldn't they be? And in some cases, that's correct. But it's important to understand that there are actually several different kinds of numerical data. The simplest way to look at the different types of numerical data is as either discrete or continuous. Discrete values have to fall into specific buckets. For example, if I go to the big box hardware store and I buy nails, I can only buy them by the box. So I can buy 1 pound or 2 pounds or 30 pounds, but I can't buy, say, 1.5 pounds. Continuous values don't have those limitations. For example, if I went to my local hardware store, I can buy a bag of nails and I can buy as many or as few as I want. So I can get 1 pound or 1.5 pounds or 1.5827632 whatever pounds. Of course, my local hardware store isn't likely to use that many decimal places, but the point is that continuous numerical values make that possible. Another way to divide up different types of numerical data is in terms of categorical or ordinal numbers. Categorical numbers are similar to discrete values in that they're buckets, but their order doesn't matter. And in fact, you can't really treat them as numbers at all. For example, zip codes are numeric, but you couldn't take advantage of a group of people's zip codes to find the center of where they live. Categorical numbers can also be used in terms of the representation question. For example, you might have a bunch of yes-no questions where the yeses are 1s and the no's are 0s. Or you might assign an index to each state in a population survey. Basically, categorical numbers are labels that happen to be numbers, but they don't really have any mathematical meaning. Ordinal numbers, on the other hand, combine categorical numbers and discrete numbers in that they represent categories, yes, but their order matters, hence the name, and you can treat them like actual numbers. One example you'll hear for this a lot are star ratings in reviews. Even though a 1-star rating is very different from a 5-star rating, you can average them together to get a general idea of what people think about a product. In the next module, we're going to move on to text data.